Welcome back. Tonight, we settle in with the patient, painstaking work of Vera Rubin, an astronomer who spent countless nights at telescope consoles in the 1970s, recording the rotation speeds of spiral galaxies, measurements that, when plotted on graph after graph, revealed something peculiar, something the equations of the day could not quite explain, a gravitational mystery hiding in the outer arms of spinning starlight, where things moved too fast, held by matter no one could see. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. On the 23rd of July, in the year 1928, in the city of Philadelphia, Pennsylvania, a child was born who would one day change the way human beings understand the structure of the universe, though of course no one could have known such a thing at the time, and the day itself was simply a warm summer day in a working-class neighborhood, with the usual sounds of streetcars and children playing and families going about their ordinary lives. The baby was named Vera, and she was the second daughter born to Philip and Rose Applebaum Cooper, a young couple who had made their home in one of the many narrow row houses that lined the streets of that part of the city, houses built of red brick and standing shoulder to shoulder, each one much like its neighbor, with small front stoops where people would sit in the evenings to escape the heat and talk quietly with those who passed by. Philip Cooper had come to America from Lithuania, carrying with him the memories of a childhood spent in a land that no longer exists in quite the same form, a place of forests and rivers and small villages where Jewish families had lived for generations, always aware of the precariousness of their position, always hoping for something more stable and safe. He had trained as an electrical engineer, a profession that required patience and precision and a certain comfort with invisible forces, with the movement of electrons through wires, with the mathematics that describe how energy could be harnessed and directed to useful ends. This understanding of unseen phenomena, of forces that could not be observed directly but whose effects could be measured and predicted, was something that would later echo in his younger daughter's own work, though neither father nor daughter could have anticipated such a connection during those early years in Philadelphia. Rose Cooper, Vera's mother, had also come from a family of Eastern European Jewish immigrants, people who had crossed the Atlantic Ocean in search of opportunity and safety, who had settled in American cities and worked to establish themselves in a new country with a new language and new customs. The immigrant experience shaped the household in subtle ways, creating an atmosphere in which education was valued above almost everything else, in which books and learning were understood to be the surest path to a better life, and in which children were encouraged to ask questions and to think carefully about the world around them. This was not a household of great wealth or luxury, but it was a household of warmth and intellectual seriousness, where a curious child would find her questions welcomed rather than dismissed. Vera's older sister Ruth had been born a few years earlier, and the two girls grew up together in that modest row house, sharing a childhood that was shaped by both the close bonds of sisterhood and the particular circumstances of the era into which they had been born. The 1930s were difficult years for many American families, and the Cooper household was no exception, as the Great Depression had settled over the country like a long gray winter, closing factories and shops, putting millions of people out of work, and creating an atmosphere of uncertainty and worry that touched even those families who managed to keep food on the table and a roof over their heads. Philadelphia, which had been a thriving industrial city, suffered along with the rest of the nation, and the neighborhoods where working people lived felt the weight of those hard times in countless more ways, in the careful stretching of every dollar, in the mending of clothes that might otherwise have been replaced, in the quiet anxiety that parents tried to hide from their children but that children often sensed nonetheless. And yet, despite the difficulties of the era, or perhaps in some ways because of them, childhood in 1930s Philadelphia had its own particular texture and rhythm, a pace of life that seems almost impossibly slow and quiet when viewed from the vantage point of later decades. The streets were filled with the sounds of horses' hooves as well as automobile engines, for the transition from one form of transportation to another was still underway, and the city retained much of its 19th century character even as it moved uncertainly into the 20th. Neighbors knew one another by name, and children played in the streets and alleyways, inventing games and forming friendships that would sometimes last a lifetime. The radio brought news and entertainment into homes that had never had such a connection to the wider world, and families would gather in the evenings to listen to programs together, creating shared experiences that bound them more closely to one another. In the Cooper household, young Vera grew from infancy into childhood with the particular blend of ordinariness and uniqueness that characterizes every human life. She learned to walk and to talk, to read and to write, to navigate the small world of her family and her neighborhood, all the while developing the distinctive personality and interests that would eventually lead her in directions no one could have predicted. She was, by all accounts, a curious child, one who noticed things that others might overlook, who asked questions that did not always have easy answers, and who seemed to possess an unusual capacity for patient observation, for watching and waiting and wondering about the nature of things. The row house where the Cooper family lived was oriented in such a way that Vera's bedroom window faced north, a geographical accident that would prove to be unexpectedly significant in shaping the direction of her young mind. The north-facing window meant that the view from her bed, when she lay awake at night as children sometimes do, was a view of the northern sky, that portion of the heavens that wheels slowly around the North Star, Polaris, the one fixed point in a turning universe. And it was through this window, during the quiet hours when she was supposed to be sleeping, that Vera first began to develop what would become a lifelong fascination with the stars. She would lie in her small bed, in her small room, in the modest row house in the working-class neighborhood of Depression-era Philadelphia, and she would watch the stars through her window, watch them for hours at a time, tracing their slow movements across the sky, noticing how they shifted position as the night progressed, how the constellations that were visible in the early evening gradually gave way to others as the Earth continued its rotation. This was not a casual or fleeting interest, not the kind of brief enthusiasm that children often develop and then abandon in favor of something new, but rather something deeper and more persistent, a genuine and abiding wonder at the nature of the universe that revealed itself each night through that north-facing window. The stars she watched were the same stars that human beings have watched for tens of thousands of years, the same points of light that ancient peoples had organized into patterns and stories, the same distant suns that had guided navigators across uncharted oceans, and that had inspired poets and philosophers to contemplate the vastness of creation. And yet, for young Vera, lying in her bed in Philadelphia in the 1930s, these stars were also something entirely personal and immediate, a source of wonder that belonged to her alone in those quiet nighttime hours, a mystery that seemed to call out for understanding and explanation. Her father, Philip, noticed his daughter's fascination with the night sky and responded with the practical ingenuity of an engineer. When Vera was around 10 years old, he built her a telescope, not the kind of sophisticated instrument that professional astronomers used, but a simple device constructed from a cardboard tube, the sort of thing that a clever and resourceful parent might assemble from materials found around the house. This homemade telescope was not powerful enough to reveal the moons of Jupiter or the rings of Saturn, but it was enough to bring the stars a little closer, to show that they were more than mere points of light, to suggest that the universe contained depths and details that the unaided eye could not perceive. For a child already captivated by the night sky, such a gift was precisely the encouragement needed to transform casual wonder into something approaching systematic inquiry. With her cardboard telescope and her north-facing window, Vera began to study the sky with increasing seriousness and attention. She learned the names of the constellations, those ancient patterns that human beings had imposed upon the random scattering of stars, and she tracked their movements through the seasons, noting how Orion dominated the winter sky while Scorpius ruled the summer, how the Big Dipper circled endlessly around Polaris, never setting below the horizon for observers in the northern latitudes. She began to understand that the apparent movement of the stars was actually a reflection of the Earth's own rotation and revolution, that the solid ground beneath her feet was itself hurtling through space at speeds that the human mind could barely comprehend, and that the stillness of night was an illusion concealing motion on a cosmic scale. She also developed an interest in meteors, those streaks of light that occasionally flash across the night sky when small fragments of rock and metal enter the Earth's atmosphere and burn up from the friction of their passage. Meteor showers, which occur when the Earth passes through the debris trails left by comets, were events of particular fascination, and Vera would stay awake late into the night to watch these celestial displays, counting the falling stars as they appeared, noting their brightness and direction, gathering data even before she had any formal training in how such data might be collected or analyzed. On nights when meteor showers were predicted, she would resist sleep with a determination unusual in a child her age, positioning herself at her window to witness as many of these brief visitors as possible, each one a tiny fragment of the solar system announcing its arrival with a momentary blaze of light. She collected meteor fragments when she could find them, though true meteorites, the pieces that survive their fiery passage through the atmosphere and actually reach the ground, are far rarer than most people realize, and the specimens she gathered may have been ordinary rocks that she hopefully identified as visitors from space. But the impulse to collect, to gather physical evidence of the phenomena that fascinated her, was significant in itself, suggesting a mind that was not content merely to observe but that wanted to understand, to hold the evidence in her hands, to make the abstract concrete and the distant near. At the local public elementary school that she attended, her teachers began to notice that this quiet, observant child had an unusual curiosity about scientific matters, a willingness to ask questions that went beyond the standard curriculum, and a capacity for concentration that set her apart from many of her peers. In an era when girls were often discouraged from pursuing interests in mathematics and science, when the prevailing assumption was that such subjects were properly the domain of boys, Vera's teachers seemed to have recognized something worth encouraging, or at least worth not actively discouraging, and she was allowed to pursue her interests without the obstacles that many young women of her generation encountered. The family's emphasis on education, rooted in the immigrant experience and in the particular values of their cultural background, provided a foundation of support for Vera's developing interests. Despite the economic hardships of the Depression, despite the constant need to be careful with money and to make do with less, Philip and Rose Cooper maintained their commitment to their daughter's education, understanding that knowledge was a form of wealth that could not be taken away, that learning was both a practical necessity and a source of meaning in an uncertain world. In this atmosphere, a child who wanted to stay up late watching stars, who asked endless questions about the nature of the universe, who collected rocks in the hope that they might be fragments of other worlds, was not seen as strange or troublesome, but as someone whose curiosity deserved to be nurtured and encouraged. And so the years of Vera's childhood in Philadelphia passed, each one adding to her store of observations and questions, each one deepening her fascination with the night sky and with the larger universe of which the Earth was such a small and fragile part. The modest row house with its north-facing window, the homemade cardboard telescope, the patient hours spent watching stars and meteors, the supportive family and the tolerant teachers, all of these elements came together to shape a mind that would one day make contributions to human knowledge that no one in those quiet Depression-era years could possibly have imagined. But for now, she was simply a young girl lying awake at night, watching the stars wheel slowly overhead, wondering what they were and how far away and what mysteries they might yet reveal to anyone patient enough to watch and careful enough to ask the right questions. When Vera Cooper was 10 years old, her family made the decision to leave Philadelphia and relocate to Washington, D.C., where her father had found promising opportunities for work in the electrical engineering field. This move, undertaken in 1938 when the country was still finding its footing after the long years of economic hardship, would prove to be one of those quiet turning points that sometimes shape a life in ways no one can anticipate at the time. The Cooper family settled into their new home, and young Vera began the process of adjusting to an unfamiliar city, new schools, and the particular rhythms of life in the nation's capital, a city quite different in character from the Philadelphia neighborhood she had known in her earliest years. Washington in the late 1930s was a city of wide avenues and grand government buildings, of monuments and museums, and of a certain formality that came from its role as the seat of national power. For a curious child with an already awakening interest in the natural world, the city offered its own particular wonders, including the Smithsonian Institution and its collections, though perhaps the most significant feature of Vera's new environment was something far simpler and more universal. The night sky over Washington, while affected by the lights of the growing city, still offered views of the stars and planets that had captivated her since those earliest nights spent gazing out her north-facing bedroom window in Philadelphia, and she continued her quiet habit of watching the heavens whenever the opportunity presented itself. Vera enrolled in the local junior high school and began navigating the social and academic landscape that all young people must learn to traverse during those transitional years between childhood and adolescence. She was a diligent student with a natural aptitude for learning, and she found herself drawn particularly to subjects that dealt with the physical world and its underlying principles, though it must be said that the educational expectations for girls in the 1930s and 1940s were often quite different from those held for boys. Young women were generally encouraged toward pursuits considered appropriate to their expected future roles, and the sciences, particularly the physical sciences, were widely regarded as masculine domains where girls might dabble but were not truly expected to excel or pursue seriously. This was simply the prevailing view of the time, held not out of particular malice but rather from long-established assumptions about the natural order of things and the proper spheres of men and women. As Vera progressed through junior high and eventually entered Coolidge High School, also located in Washington, D.C., she began to encounter more directly the subtle and sometimes not so subtle barriers that the era placed before girls who showed interest in scientific pursuits. The message conveyed through countless small interactions and institutional assumptions was that while it was perfectly acceptable for a young woman to appreciate science in a general way, to find it interesting as one might find poetry or history interesting, the serious study and professional practice of scientific disciplines was something best left to men. This was particularly true of fields like physics and astronomy, which dealt with the vast impersonal forces of the universe and required mathematical rigor of the sort that many people of that era genuinely believed lay beyond the natural capabilities of the female mind. Such beliefs seem strange and even bewildering to us now, but they were woven deeply into the fabric of mid-20th century American society, and young women who aspired to scientific careers faced them at nearly every turn. It was during her time at Coolidge High School that Vera experienced one of those discouraging encounters that so many women of her generation would later recall when reflecting on their paths into science. Her physics teacher, a man whose name has not been preserved in the historical record with the same care given to his more supportive colleagues in Vera's later education, learned of her interest in astronomy and her intention to pursue it as a serious course of study. Rather than offering encouragement or guidance, he attempted to redirect her ambitions towards something he considered more suitable, more practical, and more appropriate for a young woman. The precise words of this discouragement have been lost to time, but the effect of such interactions on young people can be profound, either crushing their aspirations entirely or, in certain resilient individuals, strengthening their resolve through a kind of quiet determination that says, almost without words, that the doubters and discouragers will be proven wrong. For Vera Cooper, the experience seems to have produced the latter effect, though at the time it must have been painful to have her genuine interests dismissed so casually by someone in a position of educational authority. Despite this discouragement, or perhaps in part because of it, Vera continued to pursue her fascination with the stars, finding support where she could and creating opportunities for herself when none were offered. One of the most significant of these self-created opportunities came in the form of a project she undertook with the help of her father, Philip Cooper. Together, they built a telescope, a modest instrument by professional standards, but a remarkable achievement for a high school student working with limited resources and whatever guidance she could find in books and other references available at the time. The process of building this telescope, of grinding and polishing lenses, of constructing a tube and mount, of aligning the optics and pointing the finished instrument at the night sky for the first time, was an education in itself. It taught Vera something about the practical challenges of astronomical observation, about the patience and precision required, and about the deep satisfaction that comes from creating a tool with one's own hands and using it to explore the universe. Her father's willingness to help with this project, to take seriously his daughter's interest in a field that others dismissed as unsuitable for her, was a gift of incalculable value, demonstrating through action rather than words that her aspirations were worthy of support. With her homemade telescope and her ever-growing curiosity, Vera continued her observations of the night sky, and she developed a particular interest in tracking the paths of meteors as they streaked across the darkness. In an act of creative record-keeping that reveals something of her systematic and persistent nature, she began mapping these meteor paths on the ceiling of her bedroom, creating a kind of personal star chart marked with the traces of these brief celestial visitors. Each line on that ceiling represented a moment of watchfulness, a connection between the young observer lying in her bed and the vast spaces through which Earth moved on its endless journey around the sun. The ceiling became a record not just of meteors but of hours spent in careful attention, of patience cultivated, of a scientific temperament being shaped through practice long before any formal training would refine it further. During these formative years, Vera also discovered a figure who would serve as an important source of inspiration and proof that women could indeed make meaningful contributions to astronomy. Through her reading, she learned about Maria Mitchell, who had lived nearly a century earlier and had become the first professional woman astronomer in the United States. Mitchell had discovered a comet in 1847 using a telescope not so different in principle from the one Vera had built with her father, and she had gone on to become a professor of astronomy at Vassar College, training generations of women students and demonstrating through decades of work that the female mind was perfectly capable of engaging with the most demanding questions of astronomical science. For Vera, learning about Maria Mitchell was a revelation of sorts, concrete evidence that the path she wished to walk had been walked before, however rarely, and that the barriers she faced were not absolute laws of nature but rather human constructions that could, with sufficient determination and ability, be overcome or at least navigated around. The discovery of Maria Mitchell also brought with it a clearer understanding of just how thoroughly male-dominated the field of professional astronomy remained. Mitchell had been an exception in her own time, and while progress had been made in the decades since, the astronomical profession in the 1940s was still overwhelmingly composed of men, with women typically relegated to secondary roles as computers, the term then used for people who performed calculations, or as assistants to male astronomers who received credit for discoveries and directed research programs. A young woman aspiring to become a professional astronomer in her own right, to make her own observations and draw her own conclusions and have those conclusions taken seriously by the scientific community, faced odds that were long indeed. Vera understood this, at least in part, during her high school years, and yet the understanding did not deter her. If anything, it seems to have clarified her determination, giving her a realistic assessment of the challenges ahead while strengthening rather than weakening her commitment to the course she had chosen. The years during which Vera attended Coolidge High School coincided with one of the most tumultuous periods in modern history, and the atmosphere of wartime Washington during World War II formed an inescapable backdrop to her adolescence. The capital was transformed by the conflict, its population swelling with military personnel and government workers, its rhythms altered by rationing and air raid drills and the constant awareness that the nation was engaged in a struggle of global significance. Young men only slightly older than Vera were going off to war, and the newspapers and radio broadcasts brought daily reports of battles fought in places most Americans had never heard of before. The war affected every aspect of life, including education, as schools adjusted their curricula and young people confronted questions about their futures against a backdrop of profound uncertainty. For Vera, these years of external upheaval were also years of internal consolidation, during which her commitment to science and astronomy crystallized into something firm and enduring, a sense of purpose that would guide her through all the challenges that lay ahead. Vera's academic abilities and dedication did not go unrecognized, despite the skepticism she encountered regarding her particular interests. She performed exceptionally well in her studies across all subjects, demonstrating the kind of broad intellectual capability that marks individuals of genuine scholarly temperament. At some point during her high school years, she entered a science competition and won an award, a validation of her abilities that must have been particularly meaningful given the discouragement she had received from her physics teacher. Such awards and recognitions, while small in the grand scheme of a scientific career, can provide crucial encouragement to young people still forming their sense of what they might accomplish in the world. And this recognition helped confirm what Vera already felt within herself, that she belonged in the world of science regardless of what others might think appropriate for someone of her gender. As her high school years drew toward their conclusion, Vera began the process of applying to colleges, seeking institutions with strong astronomy programs where she might continue her studies and begin the long preparation for a professional career. This process brought her into contact once again with the skepticism and doubt that attended any young woman's aspirations towards science in that era. The very idea that a girl would seriously pursue astronomy as a career, rather than treating it as a pleasant hobby to be set aside upon marriage and motherhood, struck many adults as peculiar at best and foolish at worst. Guidance counselors and others in positions to offer advice may have suggested more practical paths, more realistic goals, careers in teaching perhaps, or nursing, or one of the other fields considered appropriate for educated women of the time. But Vera had made her decision, and she proceeded with her applications despite whatever doubts others expressed, looking for a place where she could study the stars and begin to make her own contributions to humanity's understanding of the cosmos. In 1944, Vera Cooper graduated from Coolidge High School with the highest academic honors her school could bestow, having earned the distinction of class valedictorian through 4 years of dedicated study and consistent excellence. This achievement was accompanied by a scholarship offer that would help make it possible for her to continue her education at the collegiate level, a practical necessity for a family of modest means during the final year of a war that had strained household budgets across the nation. At the age of 16, standing at the threshold of adulthood with the Second World War still raging and the future uncertain in so many ways, Vera Cooper had completed her secondary education and was ready to take the next step toward becoming an astronomer. The discouragement and skepticism she had encountered had not deterred her, but had instead helped forge the quiet determination that would characterize her entire career. She had built a telescope with her own hands, mapped meteor paths on her ceiling, found inspiration in the example of Maria Mitchell, and proven through her academic achievements that she possessed the intellectual capabilities necessary for scientific work. What remained to be seen was whether the institutions of higher education and the professional world of astronomy would give her the opportunity to demonstrate what she could accomplish when given the chance to work. The young woman who had spent so many nights watching the stars from her bedroom window was about to begin the formal training that would eventually enable her to reveal secrets of the universe that no one yet suspected were waiting to be found. In the autumn of 1944, a young woman of 16 years arrived in Poughkeepsie, New York, carrying with her a small collection of belongings and a rather large collection of hopes concerning the stars. Vera Cooper had chosen Vassar College with considerable deliberation, and her reasons for this choice tell us something meaningful about the way inspiration travels across generations, passing from one mind to another like starlight crossing the vast distances between galaxies. She had selected Vassar specifically because it was the institution where Maria Mitchell had once taught, and because it possessed the first astronomical observatory ever established at a women's college in the United States, a distinction that mattered deeply to a young person who wished to study the universe and who happened to be female in an era when such combinations were regarded as unusual at best and impossible at worst. Maria Mitchell had died more than half a century before Vera Cooper set foot on the Vassar campus, yet her presence lingered in ways both tangible and otherwise. Mitchell had been the first professional female astronomer in America, a woman who discovered a comet in 1847 and subsequently joined the Vassar faculty when the college opened its doors in 1865. She had spent nearly 2 decades teaching young women that the heavens were not closed to them, that the precise measurement of celestial positions and the patient observation of variable stars were activities as suitable for female minds as for male ones. The observatory she had used still stood on the campus grounds, a small domed building that had witnessed countless hours of careful watching and recording. When Vera Cooper learned of this history during her years at Coolidge High School in Washington, D.C., she felt a connection to something larger than herself, a tradition of women looking upward and taking notes on what they saw. The Vassar campus in 1944 was a place of red brick buildings and spreading trees, of academic traditions and wartime anxieties existing side by side. The Second World War was still underway when Vera arrived, though its end would come less than a year later, and the campus atmosphere carried that particular mixture of solemnity and determination that characterized American educational institutions during those years. Young women studied their subjects with perhaps an extra measure of seriousness, aware that the world beyond the college gates was engaged in matters of tremendous consequence. Yet within the classrooms and laboratories, the ordinary business of learning continued, which is to say that equations were solved and papers were written and examinations were taken, much as they had been in calmer times and would be in calmer times to come. The astronomy department at Vassar was chaired during these years by Maud Makeimson, a woman whose own life had taken several unusual turns before arriving at academic respectability. Professor Makeimson had come to astronomy later than most, raising 4 children before completing her doctoral studies at the University of California in Berkeley. She was a specialist in celestial mechanics and archaeoastronomy, with particular interests in how ancient peoples had understood and tracked the movements of heavenly bodies. Under her guidance, the astronomy program at Vassar maintained the rigorous standards that Maria Mitchell had established decades earlier, expecting its students to master not only the poetry of the cosmos but also the mathematics that made precise understanding possible. Vera Cooper became a student of Professor Makeimson and found in her both an instructor and an example. The courses she took were demanding in the manner of serious scientific education, requiring facility with calculus and physics alongside the specific techniques of astronomical observation and analysis. She learned to use telescopes and to reduce observational data, to calculate orbits and to understand the physical principles governing the behavior of stars. The mathematics was sometimes difficult, as mathematics often is, but she persisted through the difficulties with the steadiness that would characterize her entire career. Physics presented its own challenges, requiring her to think about matter and energy and the forces that govern their interactions, concepts that would prove essential when she later turned her attention to the dynamics of galaxies. What made Vera Cooper somewhat unusual among her Vassar classmates was not simply her aptitude for these subjects, but her single-minded focus upon them. When she graduated in 1948, she would be the only astronomy major in her class, a circumstance that reflects both her particular devotion to the field and the relative rarity of young women choosing such a path even at an institution with Vassar's astronomical heritage. Most of her fellow students were preparing for other futures, whether in teaching or in the various domestic arrangements that society expected of educated women in that era. Vera Cooper was preparing to become an astronomer, which is a different sort of preparation altogether. The post-war years that encompassed her junior and senior terms brought a particular optimism to American campus life. The war had ended in 1945, and young men were returning from military service to resume interrupted educations or to begin new ones under the provisions of the GI Bill. The terrible anxieties of wartime gave way to a sense of possibility, a feeling that the future might hold good things if one worked diligently toward them. This optimism did not eliminate all the constraints that society placed upon women's ambitions, but it did create an atmosphere in which ambitious young people of all sorts felt entitled to dream somewhat larger dreams than their predecessors had dared to imagine. Campus life at Vassar during these years followed patterns that would seem both familiar and strange to contemporary observers. The students attended classes and studied in the library and took their meals together in the dining halls. They formed friendships and participated in various extracurricular activities and occasionally worried about their grades. There were dances and lectures and the small dramas that always accompany communities of young people living in close proximity. The war's end had brought a certain lightness to these activities, a sense that ordinary pleasures were permissible again after years of national sacrifice. Yet the college retained its academic seriousness, continuing to expect rigorous work from its students regardless of whatever social events might occur on the weekends. It was during this period that Vera Cooper met a young man named Robert Joshua Rubin, though the meeting took place not on the Vassar campus but on a bus, which is perhaps a more democratic setting for such encounters. They were introduced by a mutual friend, one of those casual connections that sometimes prove more consequential than anyone anticipates at the moment. Robert Rubin was a graduate student in chemistry at Cornell University, located some distance away in Ithaca, New York. He was intelligent and kind, qualities that tend to matter more in the long run than the more dramatic attributes that sometimes catch young people's attention. The introduction led to conversation, and the conversation led to further meetings, and the courtship that developed over Vera's junior and senior years followed the patterns of such relationships in that era, involving letters and occasional visits and the gradual deepening of mutual affection. Throughout this period of personal development, Vera Cooper continued her astronomical work with undiminished dedication. The Vassar Observatory, that small domed building connected to Maria Mitchell's legacy, became a familiar place to her. She observed there regularly, spending hours at the telescope in the particular silence that astronomical work requires. Observing is largely a matter of patience and precision, of waiting for the right conditions and then recording what one sees with careful accuracy. The night sky over Poughkeepsie offered her views of the same objects that astronomers everywhere were studying, the stars and nebulae and distant galaxies that constituted the observable universe as it was understood in the 1940s. She learned to operate the equipment and to interpret her observations, skills that would serve her well in the decades of research that lay ahead. Her undergraduate thesis concerned the distribution of galaxies, which is to say that even at this early stage of her education, she was thinking about the large-scale structure of the universe. Galaxies are collections of billions of stars bound together by gravity, and the way they are distributed through space tells us something fundamental about the history and nature of the cosmos. Are they scattered randomly, like seeds blown by the wind, or do they cluster together in patterns that reveal underlying physical processes? These were questions that astronomers were actively investigating during the 1940s, and Vera Cooper contributed to this investigation through her undergraduate research. The thesis demonstrated her ability to engage with serious scientific questions and to pursue them with appropriate methodological care. In 1948, she graduated from Vassar College with a Bachelor of Arts degree in astronomy, having earned the distinction of Phi Beta Kappa membership in recognition of her academic excellence. Phi Beta Kappa is the oldest academic honor society in the United States, and election to its membership indicates performance of the highest caliber. Vera Cooper had proven herself capable of meeting the most demanding standards that Vassar could set, and she had done so while maintaining her focus on a field that few women entered and fewer still pursued as a lifelong vocation. The day after her graduation, she married Robert Rubin in a ceremony that joined her personal life to the man who would prove to be her steadfast partner for more than 6 decades. The timing of this wedding, following so immediately upon her academic achievement, might seem to suggest that marriage was replacing ambition, that she was exchanging one life for another in the manner that society often expected of educated women in that era. But this was not at all what Vera Cooper Rubin had in mind. She intended to continue her studies and to become a professional astronomer, and Robert Rubin supported this intention completely. Their marriage was not a conclusion but a beginning, a partnership that would sustain both of them through the various challenges and satisfactions that lay ahead. She had already begun to explore possibilities for graduate study, And in this exploration, she encountered one of the more discouraging obstacles that female scientists regularly faced during this period. She applied to the graduate astronomy program at Cornell University, a reasonable choice given that her new husband was completing his own graduate work there. The response from Cornell was negative, and the reason given was straightforward in its discriminatory logic. The astronomy department did not accept women into its graduate program. This was stated not as an evaluation of her qualifications, which were excellent, but as a simple matter of policy. Women were not admitted, and therefore she could not be admitted, regardless of her academic record or her evident capability. This rejection must have been painful, though accounts of Vera Rubin's life do not dwell extensively on her emotional responses to such setbacks. What we know is that she did not allow the rejection to end her aspirations. Cornell's astronomy department might not accept women, but other institutions had different policies, and she would find her way to one of them. The rejection became not a barrier but merely an obstacle to be circumvented, one of many such obstacles that she would encounter and overcome throughout her career. The tradition of Maria Mitchell that had drawn her to Vassar was not merely a historical curiosity but a living example of what was possible when talented women refused to accept the limitations that others tried to impose upon them. And so Vera Rubin, née Cooper, left Vassar College as the only astronomy major of her graduating class, as a Phi Beta Kappa scholar, as a new bride, and as a young woman whose path to professional astronomy had just been blocked by one of the country's most prestigious universities. She carried with her the training she had received under Maud Makehamson, the observational experience she had gained at the Vassar Observatory, and the intellectual interests that her undergraduate thesis had begun to develop. She carried also the example of Maria Mitchell, who had shown that women could be astronomers, and the support of Robert Rubin, who believed in her capabilities without reservation. The road ahead would require persistence and creativity, but these were qualities she possessed in abundance, as she would demonstrate repeatedly in the years to come. When Vera arrived at Cornell University in the autumn of 1948, she carried with her both a quiet determination and the fresh sting of rejection, though she had learned already at 20 years old that closed doors sometimes lead to unexpected corridors, and that the path toward understanding the universe rarely follows a straight line. The astronomy department at Cornell had declined her application for graduate study, a decision that seemed to reflect not any deficiency in her abilities or her preparation, but rather the prevailing attitudes of the time regarding where women belonged in the sciences, and more specifically, where they did not belong. Princeton's graduate astronomy program, which she had also considered, did not admit women at all, a policy that would remain in place for decades to come. And so the options available to a young woman wishing to study the stars were considerably narrower than those afforded to her male colleagues, though Vera did not allow this narrowing to diminish her ambitions or redirect her gaze away from the distant galaxies that had captivated her since childhood. The physics department at Cornell, however, proved more welcoming, or perhaps simply less encumbered by tradition in this particular regard. And it was there that Vera enrolled to pursue her master's degree, joining her husband Robert, who was already engaged in doctoral research in physical chemistry at the same institution. The couple had married in 1948, shortly after Vera's graduation from Vassar, and their early married life unfolded within the particular rhythms of graduate student existence, with its modest accommodations and its demanding schedules and its peculiar blend of intellectual excitement and financial constraint. Robert's presence at Cornell meant that Vera could continue her studies while maintaining the partnership that would sustain her throughout her career, and the two young scientists found themselves building a life together in Ithaca, New York, surrounded by the steep gorges and grey winters of that region, pursuing their respective researches with the earnestness characteristic of those early post-war years when science seemed to promise so much and the universe appeared to be yielding its secrets at an accelerating pace. At Cornell, Vera came under the mentorship of Philip Morrison, a theoretical physicist whose interests ranged across an unusually broad spectrum of topics and whose openness to unconventional ideas would prove significant for her development. Morrison had worked on the Manhattan Project during the war and had witnessed the first nuclear test at Trinity, experiences that had marked him deeply and informed his subsequent commitment to arms control and scientific responsibility, though his teaching and research continued with undiminished energy in the post-war years. He possessed that rare quality in a mentor of being genuinely interested in the questions his students wished to ask rather than merely directing them toward problems he himself had already identified as worthy. And this intellectual generosity created space for Vera to pursue the astronomical questions that truly captured her imagination, even though she was enrolled technically in the physics department rather than among the astronomers who had declined to admit her. Martha Starr Carpenter also served as an important figure in Vera's graduate education, providing both astronomical expertise and the example of a woman who had carved out a place for herself in a field that offered few welcome mats for female scholars. Carpenter worked on stellar astronomy and had navigated the academic landscape with its particular obstacles for women scientists, and her presence on Vera's thesis committee represented something valuable beyond mere technical guidance, though that guidance was itself considerable. The combination of Morrison's theoretical breadth and Carpenter's astronomical grounding gave Vera a foundation from which to attempt something rather bold for a master's thesis, something that would draw skepticism and even hostility from the broader astronomical community, though also the attention of at least one prominent figure whose curiosity outweighed his caution. The thesis topic that Vera chose to investigate concerned the motions of galaxies, not simply the motions that Edwin Hubble had documented in his landmark work establishing that the universe was expanding, but rather an additional layer of motion that might exist beyond or beneath that expansion. Hubble had shown that galaxies recede from one another at velocities proportional to their distances, a relationship now known as Hubble's law, and this discovery had revolutionized cosmology by demonstrating that the universe was not static but dynamic, not eternal and unchanging but evolving through time from some initial condition toward some future state. What Vera wondered, with the particular kind of wondering that characterizes genuine scientific inquiry, was whether the galaxies might also be rotating around some unknown center, whether there might be large-scale streaming motions superimposed upon the general expansion, patterns of cosmic flow that would reveal additional structure in the distribution and movement of matter throughout the universe. This was, in 1949 and 1950, a rather audacious question for anyone to ask, let alone a young woman pursuing her first graduate degree at an institution that had not even admitted her to its astronomy program. The prevailing view held that the expansion Hubble had measured accounted adequately for galactic motions, that once you subtracted the effects of this expansion, the remaining velocities of galaxies would prove to be essentially random, small perturbations around the smooth Hubble flow rather than systematic drifts in preferred directions. To suggest otherwise was to challenge the emerging consensus in cosmology, and consensus in science, while never absolute, carries considerable weight, particularly for those who have spent their careers constructing it, and who might reasonably feel that newcomers should demonstrate some deference before proposing alternatives. Vera gathered what data she could find on galactic velocities, compiling measurements from various sources and analyzing them for patterns that might indicate rotation or streaming beyond the Hubble expansion. The data available in that era were sparse and noisy by modern standards, the uncertainties large, the samples small, and the systematic errors difficult to assess. Yet Vera discerned what appeared to be hints of precisely the large-scale motion she had hypothesized, suggestions that galaxies in certain regions of the sky moved with correlated velocities that could not be explained by expansion alone. The analysis was preliminary, the conclusions tentative, the caveats numerous, as befits any scientific work at the edge of available evidence. Yet the underlying question was profound, for if such motions existed, they would imply the presence of vast concentrations of matter exerting gravitational influence across enormous distances, matter whose nature and distribution remain to be determined. In December of 1950, Vera presented her findings at a meeting of the American Astronomical Society held in Haverford, Pennsylvania, an occasion that would prove memorable for reasons both professional and personal. She was 22 years old. She was pregnant with her first child, and she stood before an audience of established astronomers, almost entirely male, to describe research that challenged assumptions many of them held dear. The reception was not warm. The questions from the audience carried an edge that went beyond ordinary scientific skepticism into something closer to dismissal, as though the work could not possibly merit serious consideration, perhaps because of its conclusions, perhaps because of who was presenting it, perhaps because of some combination of factors that the questioners themselves might not have fully examined. Vera recalled later the hostility in the room, the sense that she was being treated not as a young colleague offering preliminary results for collegial discussion, but as an interloper who had wandered into territory where she did not belong and had the temerity to suggest that the residents had overlooked something important. The male-dominated character of astronomy in that era cannot be overstated, for it shaped not only who received opportunities and recognition, but also how ideas were evaluated and how dissent was handled. A young woman presenting unconventional results faced obstacles that her male counterparts did not encounter, subtle and not so subtle signals that her presence was anomalous, that her ideas were presumptuous, that she ought perhaps to content herself with lesser ambitions, or at least to wait until more senior figures had validated her approach before daring to speak at professional meetings. The isolation Vera felt at Haverford was compounded by her physical condition, for pregnancy in academia was itself treated as somewhat irregular in those years, a biological circumstance that marked a woman as different, as temporarily or perhaps permanently diverted from the single-minded dedication that serious science was thought to require. She stood before her critics carrying both an unpopular thesis and an unborn child, embodiments of her refusal to choose between intellectual and personal fulfillment, between the life of the mind and the life of the body. Not everyone in the audience responded with hostility, however, and one figure in particular found himself intrigued by what the young woman from Cornell was suggesting. George Gamow, the Ukrainian-born physicist who had made fundamental contributions to nuclear physics and cosmology, who had proposed the hot Big Bang model and predicted the cosmic microwave background radiation, listened to Vera's presentation with the kind of attention that great scientists sometimes reserve for ideas that others dismiss too quickly. Gamow possessed a playful brilliance and a willingness to entertain heterodox notions, qualities that had served him well in his own work on nucleosynthesis and the early universe. And something in Vera's analysis caught his interest, planted a seed that would bear fruit in the coming years when their paths crossed again. His intrigued response stood out against the backdrop of skepticism and provided Vera with at least one signal that her work might not be entirely without merit, that someone whose judgment she respected found the questions worth asking even if the answers remained uncertain. Her son David was born in 1950. The first of 4 children who would arrive over the coming decade, and the rhythms of new motherhood intertwined with the rhythms of thesis completion in ways that academia was not designed to accommodate. Vera fed her infant and analyzed her data, rocked her baby to sleep and pondered the motions of galaxies, navigated the exhaustion of early parenthood, while preparing to defend her research before a committee that would decide whether her work merited a degree. The isolation she experienced was multifaceted, arising not only from the hostile reception of her ideas, but also from the structural realities of being a young mother in an environment built around the assumption that serious scholars were men without caregiving responsibilities, men who could work late into the evening and travel freely to conferences and devote themselves without distraction to their research. Vera found herself occupying a liminal position, neither fully integrated into the community of astronomers who had rejected her application, nor entirely at home among the physicists who had admitted her, and now marked additionally by the visible evidence of her maternal status, which some regarded as incompatible with genuine scientific ambition. She completed her master's degree in 1951, successfully defending the thesis that had provoked such controversy at Haverford, and emerged from Cornell with credentials that reflected both her abilities and the obstacles she had overcome. The thesis topic that had met with skepticism and ridicule would prove, decades later, to be remarkably prescient, for the large-scale streaming motions of galaxies became an active area of research in the 1970s and beyond, as astronomers mapped the peculiar velocities of thousands of galaxies and discovered precisely the kinds of coherent flows that Vera had tentatively identified in her master's work. The existence of vast structures such as the Great Attractor, enormous concentrations of mass that pull galaxies toward them across hundreds of millions of light-years, confirmed that the universe possesses exactly the kind of additional organization beyond simple Hubble expansion that Vera had hypothesized, though she received little credit for having raised the question so early and so clearly. Following Robert's completion of his doctorate in physical chemistry, the young family relocated to Washington, D.C., where he had accepted a position at the Applied Physics Laboratory at Johns Hopkins University. The move took Vera away from Cornell, away from the mentors who had supported her work, and deposited her in a new city with a small child and an uncertain professional future. Washington offered proximity to various scientific institutions, yet it also presented fresh challenges for a young woman seeking to continue her astronomical research while raising a family, challenges that would require the same persistence and adaptability that had carried her through her years at Cornell. The thesis on galaxy rotation and large-scale streaming remained a document of unfulfilled promise, a harbinger of discoveries yet to come, and Vera herself remained a young scientist whose best work lay ahead of her, waiting in the turning of distant galaxies and in the patient accumulation of data that would eventually reveal what she had glimpsed so early and so dimly in those first uncertain analyses. In the autumn of 1951, Vera Rubin enrolled in the doctoral program in astronomy at Georgetown University, and this choice, like so many of the choices she would make throughout her long career, was shaped equally by scientific aspiration and by the practical realities of her life as a young mother living in the Washington area. Georgetown was, at that time, the only university in the District of Columbia and its surrounding region that offered a doctoral degree in astronomy, and so the decision was made for her in some respects by geography itself, by the simple constraint of what was possible given where she lived and what she needed to accomplish. Her husband Robert had taken a position in the area. Their young son David was still very small, and the family had settled into the rhythms of early parenthood in a modest home in the Maryland suburbs. The question of where Vera might pursue her doctorate was therefore not a question of choosing among many excellent programs scattered across the country, not a question of weighing the relative merits of one prestigious department against another, but rather a question of whether she could find any program at all that would allow her to continue her education while remaining close to her family and fulfilling her responsibilities as a mother? Georgetown University answered that question, though the answer came with its own set of complications and demands that would have discouraged many people, and that required from Vera a particular kind of quiet determination, a willingness to adapt herself to circumstances that were far from ideal, while never losing sight of the work she wanted to do. The astronomy program at Georgetown held its graduate classes in the evenings, which meant that Vera could spend her days caring for David and managing the household. And then, as the sun set and the evening darkness settled over the suburban streets, she would leave her son in Robert's care and drive alone to the university for her classes. This arrangement was both a solution and a hardship, a way of making the impossible possible while also extracting a cost that accumulated slowly over the months and years of her doctoral work. Robert, who understood Vera's ambitions and supported them with a steadiness that would characterize their entire marriage, took over the evening routines of feeding and bathing and putting their son to bed, and Vera drove through the darkness toward the lights of the Georgetown campus, where she would sit in lecture halls and seminar rooms and absorb the knowledge she needed to become an astronomer. The drive itself was not a trivial thing, not a simple matter of traveling from one place to another along well-lit highways filled with other commuters making their way home from work. In the early 1950s, the roads connecting the Maryland suburbs to the District of Columbia were often dark and winding, and Vera made this journey alone, night after night, steering her car through the pools of shadow between street lamps and watching for the occasional headlights of other vehicles approaching from the opposite direction. There is something both lonely and meditative about driving alone at night, about the way the darkness closes in around the small illuminated space of the car's interior, and the mind is left to wander through whatever thoughts present themselves during the long minutes between one turn and the next. Vera would have had time to think about the lectures she was about to attend, about the problem sets waiting to be completed, about the baby sleeping at home and the husband who had taken on the evening responsibilities so that she could pursue this peculiar dream of studying the stars. She would have had time to notice the tiredness settling into her body after a day of caring for a young child, and she would have had time to push that tiredness aside and remind herself that the evening's work still lay ahead, that the learning she sought would not come to her but had to be pursued and claimed through her own effort. At Georgetown, Vera found herself once again in the position of being one of very few women, and often the only woman, in the rooms where astronomy was taught and discussed. The isolation of this position was something she had experienced before, at Cornell, and something she would continue to experience throughout her career, a persistent background condition that colored her interactions with colleagues and shaped the way she moved through professional spaces. The other graduate students were men. The professors were men. The visiting lecturers and the members of dissertation committees were men. And Vera sat among them with her notebooks and her questions, doing the work of becoming a scientist while also carrying the additional burden of being visibly different from everyone around her. This difference was not something that could be set aside or forgotten, not something that became invisible with time and familiarity, but rather something that was present in every seminar, every office hour, every casual conversation in the hallways between classes. Vera did not allow this isolation to discourage her, but she felt it nonetheless, and the feeling became part of the texture of her graduate experience, woven into the fabric of her memories of those years alongside the equations and the observations and the slow accumulation of understanding. The astronomy program at Georgetown was small and somewhat unusual in its structure, and Vera's doctoral work would come to be supervised by one of the most colorful and influential figures in 20th century cosmology, a Ukrainian-born physicist named George Gamow, whose contributions to our understanding of the universe had already secured his place in the history of science. Gamov was not actually a member of the Georgetown faculty, but rather a professor at George Washington University, located elsewhere in the city, and he commuted to Georgetown to serve as Vera's thesis advisor, adding yet another layer of unconventionality to an arrangement that was already quite far from the standard model of doctoral education. Gamov was famous for many things, including his early theoretical work on the Big Bang and his prediction of the cosmic microwave background radiation that would eventually be detected a decade later and would confirm many of his ideas about the early universe. He was also famous for his playful personality, his love of jokes and puzzles and clever wordplay, and his habit of conducting scientific discussions in a manner that was informal and digressive and filled with unexpected tangents that nevertheless somehow led back to the central questions being considered. Vera's meetings with Gamov often took place not in a formal office on campus but in his home, where the atmosphere was relaxed and the conversation could flow in whatever direction seemed most interesting at the moment. Gamov would sit with her and talk about cosmology and galaxies and the large-scale structure of the universe, and he would encourage her to think boldly and to ask questions that others might consider too ambitious or too far outside the accepted boundaries of the field. His mentorship style was not the careful, structured guidance that some students might prefer, with regular meetings and clear milestones and detailed feedback on drafts and calculations, but rather something more like an ongoing conversation between two curious minds, one of whom happened to have decades more experience than the other. Gamov treated Vera as a fellow thinker, as someone whose ideas were worth taking seriously, and this respect from such a distinguished scientist must have been a source of encouragement during the long, difficult years of her doctoral work. He did not seem to notice or care that she was a woman in a field dominated by men, or if he noticed, he did not allow it to affect his assessment of her abilities or his willingness to invest his time and attention in her development as a scientist. The topic Vera chose for her dissertation was the spatial distribution of galaxies across the observable universe, a question that might sound abstract but that carries profound implications for our understanding of how the cosmos is organized and how it came to be the way we observe it today. At the time, the prevailing assumption among most astronomers was that galaxies were distributed more or less randomly throughout space, scattered like grains of sand thrown across a vast dark beach with no particular pattern or structure to their arrangement. Vera's dissertation challenged this assumption by examining the available data on galaxy positions and searching for evidence of non-random clustering, for signs that galaxies might be gathered together in groups and clusters, and perhaps even larger structures that spanned enormous distances across the sky. This was painstaking work, requiring her to compile catalogues of galaxy positions and to perform statistical analyses that would reveal whether the observed distribution could have arisen by chance or whether some other process must have been at work, drawing galaxies together into the aggregations that we now know to be a fundamental feature of cosmic structure. In the midst of this demanding research, in 1952, Vera gave birth to her second child, a daughter named Judith, who would be known within the family as Judy. The arrival of a new baby brought all the joys and exhaustions that accompany early parenthood, and Vera now found herself balancing her doctoral work not against the needs of one child but against the needs of two, one a toddler and one an infant, both requiring the constant attention and care that young children demand. The nighttime drives to Georgetown continued. The classes and seminars continued. The long hours of research and analysis continued. And now there was also a baby to nurse and comfort and rock to sleep in the small hours of the morning when the rest of the household was quiet and dark. Robert continued to support Vera's work with the same steadiness he had shown from the beginning, taking on his share of childcare and more than his share on the evenings when she drove into the city for her classes. But even with his help, the demands on Vera's time and energy were immense, and she met them with a quiet persistence that would become one of the defining characteristics of her entire life. The family had by this time settled into a home in suburban Maryland, in one of the communities that were growing up around the edges of Washington as the post-war expansion drew more and more people to the capital region. This was the landscape of Vera's daily life during her doctoral years: the houses and yards and shopping centers of the suburbs, the quiet streets where children played and neighbors chatted over fences, and the rhythms of domestic life unfolded in their familiar patterns. It was from this ordinary suburban setting that Vera drove each evening into the city, leaving behind the world of diapers and high chairs and bedtime stories, and entering the world of equations and observations and arguments about the nature of the universe. The contrast between these two worlds was sharp, and yet for Vera they were not separate lives but rather two aspects of a single life, two dimensions of her existence that she held together through determination and organization, and the simple refusal to accept that she had to choose one or the other. In 1954, at the age of 26, Vera Rubin completed her doctorate and became one of the very few women in the United States to hold a PhD in astronomy. Her dissertation committee included Gamow and several other notable physicists, men whose names were well known in the scientific community and whose approval signified that Vera's work had met the highest standards of the field. The thesis itself presented clear evidence that galaxies were not randomly distributed but were instead clustered together in ways that could not be explained by chance alone. This finding was, like her earlier work on galaxy rotation at Cornell, somewhat ahead of its time, and the reception it received from the astronomical community was largely dismissive. Most astronomers of the era were not prepared to accept that large-scale structure existed in the universe, that galaxies might be organized into clusters and superclusters and walls and voids that stretched across millions of light-years. The prevailing cosmological models assumed a universe that was smooth and homogeneous on large scales, and Vera's evidence of clustering seemed to contradict this comfortable assumption. As with so many of her contributions to science, this early work on galaxy clustering would eventually be vindicated by later observations and by the gradual accumulation of evidence that could not be ignored. In the decades following Vera's dissertation, astronomers would come to understand that the clustering of galaxies is indeed a fundamental feature of cosmic structure, that the universe is not a smooth featureless expanse but rather a complex web of matter organized into filaments and clusters and vast empty regions that reflect the processes by which structure formed in the early universe. The seeds of this understanding were present in Vera's 1954 dissertation, planted there by her careful analysis and her willingness to follow the data wherever it led, even when it led to conclusions that others were not ready to accept. She did not know, as she defended her thesis before her committee and received their approval and celebrated this milestone with her family, that the work she had done was a harbinger of discoveries yet to come, a first glimpse of truths about the universe that would take decades to be fully recognized and appreciated. After Vera Rubin completed her doctoral work at Georgetown University in 1954, she found herself in a position that was, in many ways, more difficult than the years of study that had preceded it. She was now Dr. Vera Rubin, holder of a doctorate in astronomy, author of a dissertation that had proposed something genuinely novel about the universe, and she was also a young mother with 2 small children, living in Washington, D.C., in a world that had very little room for women who wished to pursue careers in the physical sciences. The years that followed, stretching from 1954 through the middle of the following decade, would be marked by professional frustration, limited opportunity, and the quiet persistence that would come to define so much of her working life. The obstacles she faced were both structural and personal, woven together in ways that made them particularly difficult to overcome. One of the most immediate barriers was a set of rules, common at many universities and research institutions during this period, that prevented spouses from holding positions in the same department or, in some cases, at the same institution entirely. These anti-nepotism policies, as they were known, were ostensibly designed to prevent favoritism in hiring and promotion, but in practice they fell almost exclusively upon women, who were far more likely than their husbands to be the ones denied employment. Robert Rubin was building his career as a physical chemist, and wherever he found work, Vera found herself automatically excluded from consideration, regardless of her qualifications, regardless of her interests, regardless of the contributions she might have made. Beyond these formal policies, there was the broader reality that most research institutions and universities simply did not hire women astronomers, or hired them only in the most marginal and temporary capacities. The field of astronomy in the 1950s remained overwhelmingly male, and the few women who had managed to establish themselves in professional positions were often relegated to the role of assistant or computer, performing calculations and observations under the direction of male colleagues, their names appearing in footnotes rather than at the tops of papers. Vera Rubin had no interest in such a role. She wished to conduct her own research, to ask her own questions, to follow the threads of inquiry wherever they might lead, and this ambition, entirely reasonable though it was, placed her at odds with the expectations of her time. In 1955, she found a position at Georgetown University, where she had completed her doctoral work just a year before. The position was that of research astronomer at the Georgetown Observatory, and while it was not a tenure-track faculty appointment, it did allow her to continue her work and to maintain some connection to the academic world. She also took on teaching responsibilities, offering courses to students who were, in many cases, only a few years younger than herself. The work was steady if not glamorous, and it provided a framework within which she could continue to think about the questions that interested her most, even if the resources available to her were modest and the recognition she received was minimal. During these same years, Vera and Robert Rubin were also raising a family, and the demands of this work were considerable. Their first child, David, had been born in 1950, while Vera was still pursuing her master's degree at Cornell. Their second child, Judith, arrived in 1952, during the early years of her doctoral studies at Georgetown. After the completion of her doctorate, two more children followed, Carl in 1956 and Alan in 1960. By the time the youngest was born, Vera Rubin was managing the responsibilities of 4 young children alongside her research and teaching, a situation that would have been challenging under any circumstances and was made more so by the limited institutional support available to women in her position. The logistics of daily life during this period were intricate and unrelenting. There were meals to prepare and dishes to wash, clothing to launder and mend, appointments to keep and errands to run. There were the illnesses that come with childhood, the school functions and parent meetings, the bedtimes and the early mornings. And there was, always, the question of how to find time for the work that mattered most to her, the calculations and the observations, the reading and the writing, the slow accumulation of evidence and the careful construction of argument. Many women in similar circumstances found that they had no choice but to set aside their professional ambitions, at least for a time, and to focus entirely on the demands of family life. Vera Rubin did not make this choice, though she understood why others did, and she never judged those who found the obstacles too great to overcome. What made it possible for her to continue was, in large part, the support of her husband. Robert Rubin believed in the importance of her work, believed in her abilities, and was willing to arrange his own life in ways that made room for her research. He took on household tasks that many men of his generation would have considered beneath their attention. He adjusted his schedule to accommodate hers. He offered encouragement during periods of frustration and celebrated with her during moments of success. Their partnership was, by all accounts, one of genuine equality, unusual for its time and essential to her ability to persevere. Without Robert's unwavering support, the path she followed would have been far more difficult, and perhaps impossible. Even with this support, the practical challenges of maintaining research momentum were substantial. Observing time at telescopes was limited and had to be scheduled well in advance, often at distant locations that required travel. The analysis of data was painstaking and time-consuming, involving calculations that had to be performed by hand or with the assistance of early computing machines that were themselves cumbersome and unreliable. Writing papers required sustained concentration, the kind that is difficult to achieve when one is interrupted every few minutes by the needs of small children. Vera Rubin learned to work in fragments, stealing hours where she could, late at night after the children were asleep or early in the morning before they woke, on weekends when Robert could take over the primary responsibilities of childcare. It was not an ideal way to conduct research, but it was the way that was available to her, and she made it work. During the late 1950s and early 1960s, she continued to publish papers on subjects related to the motions of galaxies, building on the work she had begun in her doctoral dissertation. She was interested in how galaxies moved through space, how they rotated, how they interacted with one another. These were questions that lay at the intersection of observation and theory, requiring careful attention to the data that could be gathered from the light of distant objects and equally careful attention to the physical principles that might explain what was observed. Her papers appeared in professional journals, were read by some number of her colleagues, and then, for the most part, disappeared into the vast archive of scientific literature, cited occasionally but not widely discussed, contributing to the slow accumulation of knowledge without attracting particular notice. This relative obscurity was, in some ways, simply the normal condition of scientific work. Most papers, even good ones, do not transform their fields. Most researchers spend their careers making incremental contributions, adding small pieces to a puzzle whose final shape will not be apparent for many years. But for Vera Rubin, the lack of attention was also a reflection of her marginal position within the profession. She was a woman working at a relatively minor observatory, without the resources or the platform that would have been available to someone at a more prestigious institution. Her ideas were not so much rejected as ignored, passed over in favor of work by researchers whose names and positions commanded greater authority. She maintained correspondence with other astronomers during these years, exchanging letters that discussed observations and interpretations, debated points of theory, and occasionally offered mutual encouragement. These connections were valuable, providing a sense of participation in a larger community even when that participation was limited by her circumstances. The letters traveled back and forth, sometimes taking weeks to arrive, carrying questions and suggestions and the occasional bit of collegial humor. Through this correspondence, Vera Rubin remained engaged with the developments in her field, even as she worked in relative isolation. The Georgetown years were, by her own later account, professionally frustrating. She had the training and the ability to do significant work, but she lacked the resources and the opportunities that would have allowed her to pursue that work as fully as she wished. She watched as male colleagues with similar or lesser qualifications moved into positions of greater responsibility, received larger grants, gained access to better equipment. She understood that the barriers she faced were not personal but structural, embedded in the assumptions and practices of institutions that had been designed by and for men. This understanding did not make the frustration easier to bear, but it did help her to recognize that her difficulties were not a reflection of her own inadequacy. At the same time, these years were intellectually formative. The constraints under which she worked forced her to think carefully about what questions were most worth pursuing, to make the most of limited observing time, to develop skills of analysis and interpretation that would serve her well in the years to come. She learned patience, not as a passive acceptance of her circumstances, but as an active strategy for enduring and eventually overcoming them. She learned to persist in the face of indifference, to continue asking questions even when no one seemed particularly interested in the answers. By the early 1960s, Vera Rubin began to seek out collaborations with other researchers who shared her interest in the kinematics of galaxies, the study of how these vast systems move and change over time. Collaboration offered the possibility of pooling resources and expertise, of gaining access to equipment and facilities that would otherwise have been beyond her reach. It also offered the intellectual stimulation of working with others who were grappling with similar problems, the chance to test ideas against the perspectives of colleagues who might see things differently. These early collaborations were modest in scale, but they represented a shift in her working life, a movement toward the kind of sustained, focused research that she had always hoped to pursue. Throughout these years, she continued to be a mother, continued to manage the complex logistics of a household with 4 children, continued to be a partner to Robert in the shared project of building a family. And in this aspect of her life, too, something remarkable was taking shape, though it would not become fully apparent until many years later. All 4 of her children, David, Judith, Carl, and Alan, would grow up to become scientists themselves, pursuing careers in fields ranging from geology to mathematics to astronomy. This outcome was not inevitable, not simply the result of genetic inheritance or parental pressure, but rather the product of a household in which curiosity was valued, in which questions were welcomed, in which the pursuit of understanding was treated as one of the most important things a person could do. Vera and Robert Rubin created an environment in which their children learned, by observation and by example, that the life of the mind was a life worth living, that the patient work of investigation and discovery was its own reward. The remarkable scientific legacy of the Rubin family, for children all finding their way into research careers, stands as a testament to the values that shaped their upbringing and to the parents who made those values manifest in the daily texture of family life. The wilderness years, as one might think of them, were drawing toward a close. By the middle of the 1960s, Vera Rubin was poised for a transition, a movement into a new phase of her career that would bring greater opportunity and, eventually, greater recognition. But the years of struggle and obscurity had left their mark, shaping her character and her approach to her work in ways that would remain visible throughout her life. She had learned what it meant to persist without encouragement, to work without resources, to believe in the value of her own questions even when the world seemed indifferent to them. These lessons would prove invaluable in the work that lay ahead. In 1965, Vera Rubin made a decision that would shape the entire remaining arc of her scientific life, accepting a position at the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, a place whose name suggested the study of Earth's magnetic field, but which had long since expanded its reach to encompass the deepest questions about the cosmos, from the nature of the atomic nucleus to the structure of distant galaxies. The Department of Terrestrial Magnetism, often referred to simply as DTM by those who work there, occupied a quiet campus in the northwest corner of Washington, D.C., set among trees and winding paths that gave it the feeling of a small retreat rather than a major research institution. And this physical setting reflected something essential about the culture within, a culture of unhurried inquiry and genuine collaboration that Rubin found immediately congenial after the sometimes fraught atmosphere of academic departments elsewhere. The Carnegie Institution itself had been founded in 1902 by Andrew Carnegie with the stated purpose of encouraging investigation, research, and discovery in the broadest and most liberal manner. And by the middle of the 20th century, it had developed a reputation for supporting scientists who pursued long-term projects requiring patience and persistence rather than quick results, which made it an ideal home for someone interested in the slow accumulation of observational data about galaxies. Unlike universities, where faculty members often found themselves navigating complex departmental politics involving tenure decisions, teaching loads, and competition for graduate students, the Carnegie Institution offered its research staff the freedom to focus almost entirely on their scientific work, with minimal administrative burdens and a collegial atmosphere in which people helped one another simply because interesting problems deserved to be solved. The director of DTM at the time understood that the best science often emerged from unexpected combinations of expertise, and he had assembled a staff that included not only astronomers but also physicists, geochemists, and skilled instrument builders, all working in close proximity so that conversations in the hallways might lead to new collaborations that no one had planned in advance. Vera Rubin would later describe this environment as one of the most supportive she had ever encountered, a place where her colleagues treated her as a fellow scientist first and foremost, where the quality of her ideas mattered more than any other consideration, and where the persistent background noise of skepticism about women in science was, if not entirely absent, at least considerably muted compared to what she had experienced at other institutions. It was at DTM that Rubin met W. Kent Ford, Jr., an encounter that would prove as consequential for astronomy as any in the latter half of the 20th century, though neither of them could have known this at the time. Kent Ford was an instrument builder of exceptional skill, a man who understood both the theoretical principles of optical design and the practical realities of machining metal and aligning delicate components, and who had devoted years of painstaking work to developing a new kind of spectrograph that could do things no previous instrument had managed. A spectrograph, as you may already know from earlier sections of this narration, is a device that spreads light into its component wavelengths, allowing astronomers to measure how fast objects are moving toward or away from us by detecting the shift in spectral lines. And the sensitivity of a spectrograph determines how faint the objects are that can be studied and how precisely their velocities can be measured. Ford had developed what was called an image tube spectrograph, which used electronic amplification to detect light far fainter than traditional photographic plates could record. And this instrument represented a genuine leap forward in observational capability, allowing astronomers to measure spectra from regions of galaxies that had previously been too dim to study at all. The image tube at the heart of Ford's spectrograph worked by converting incoming photons into electrons, amplifying this electronic signal, and then converting it back into light that could be recorded on photographic film, with the result that exposures that would have taken many hours with conventional methods could now be completed in a fraction of the time. And even more importantly, that light from the faint outer regions of galaxies could be captured at all. When Rubin arrived at DTM, Ford had already built this remarkable instrument, but he was looking for interesting scientific problems to which it might be applied. And Rubin had exactly such problems in abundance, born from her long-standing fascination with the motions of galaxies and the structures within them. Their partnership emerged naturally from this complementary set of interests and abilities, with Ford providing the instrumental expertise and Rubin providing the astronomical knowledge and scientific questions. And together they formed a collaboration that would last for decades and produce some of the most important observational results in 20th century astronomy. Ford was, by temperament and training, a builder and problem solver who found deep satisfaction in making instruments work better than anyone thought possible, while Rubin was driven by curiosity about the physical processes governing the universe, and their mutual respect allowed them to work together without the friction that sometimes develops when people with different skills must depend on one another. The collaboration began with a shared understanding that Ford's spectrograph opened up new possibilities for studying galaxies, and specifically for measuring how galaxies rotate, which is to say how fast the stars and gas at different distances from the galactic center are moving around that center, like horses on a carousel that might or might not be moving at the same speed. To understand why this mattered, it helps to know that astronomers had long assumed that galaxies would rotate in a way similar to the solar system, where planets close to the Sun orbit quickly while planets far from the Sun orbit slowly, a pattern that follows directly from the laws of gravity when most of the mass is concentrated at the center. If galaxies worked the same way, with most of their mass concentrated in the bright central bulge where most of the stars are visible, then stars and gas clouds in the outer regions of galaxies should orbit more slowly than those closer to the center, producing what astronomers call a Keplerian rotation curve in honor of Johannes Kepler, who first described this pattern for planetary orbits. But to test whether galaxies actually behave this way required measuring the velocities of gas and stars not just in the bright central regions, where observations were relatively easy, but also in the faint outer regions, where the light was so dim that previous instruments had been unable to make reliable measurements. And this was precisely the capability that Ford's image tube spectrograph provided. With this instrument mounted on a sufficiently large telescope, Rubin and Ford could point at a galaxy, position the spectrograph slit along the galaxy's major axis, and measure the Doppler shift of light from many different positions along that axis, building up a picture of how fast different parts of the galaxy were rotating, from the center all the way out to the faint edges where the surface brightness dropped to almost nothing. In 1965, the same year she joined DTM, Rubin became the first woman permitted to observe at Palomar Observatory in California, home to the 200-inch Hale telescope, which was then the largest optical telescope in the world and remained a premier observing facility where astronomers competed for precious nights of observing time. The journey from Washington to the mountains of Southern California, the drive up the winding road to the observatory dome, and the ritual of preparing for a night of observation at such a storied facility would have been exciting for any astronomer. But for Rubin, it carried the additional weight of being the first of her gender to be granted access to this particular cathedral of science, a milestone that she approached with characteristic pragmatism and good humor. The story of her first visit to Palomar includes a small detail that illustrates both the absurdity of the barriers she faced and her practical approach to overcoming them. For when she arrived at the observatory, she discovered that there was no women's restroom anywhere in the building, which was perhaps not surprising given that no one had thought to provide one during the decades when women were simply not permitted to observe there. Rather than make a formal complaint or draw attention to the problem in a way that might have marked her as difficult, Rubin found a piece of paper, cut it into the shape of a skirt, and taped it to the figure on the door of the men's restroom, thereby creating, through this simple and slightly whimsical act, a women's restroom where none had existed before. This small gesture captured something essential about her approach to the obstacles she encountered throughout her career, a willingness to acknowledge the absurdity of the situation while simply getting on with the work she had come to do, refusing to let the pettiness of institutional neglect distract her from the science that mattered. With access to Palomar and other major observatories, and with Ford's spectrograph in hand, Rubin began a systematic study of the Andromeda Galaxy, known to astronomers as M31, which was in many ways an ideal target for this kind of investigation. Andromeda is the nearest large spiral galaxy to our own Milky Way, close enough that its individual stars can be resolved in large telescopes and its structure can be studied in considerable detail, yet far enough away that we can see it from outside, giving us a perspective on its overall shape and rotation that we cannot easily achieve for our own galaxy, which we are embedded within. The galaxy appears as an elongated oval in the night sky, tilted at an angle to our line of sight, and this inclination means that the Doppler shifts caused by its rotation are large enough to measure with precision, as stars and gas on one side of the galaxy are moving toward us while those on the other side are moving away. During observing runs at Kitt Peak and Palomar and other observatories through the late 1960s, Rubin and Ford accumulated spectra from dozens of positions along the major axis of Andromeda, carefully measuring the wavelengths of emission lines from clouds of ionized hydrogen gas and absorption lines from the integrated light of millions of stars, building up point by point a detailed picture of how the galaxy's rotation velocity changed with distance from the center. The work was painstaking and required long hours at the telescope, sitting in the cold dome through the night, periodically checking the guiding to make sure the faint galaxy light was falling precisely on the spectrograph slit, and then returning home to develop the photographic plates and measure the spectral lines with the meticulous care that valid scientific results require. What began to emerge from these measurements was unexpected, for as Rubin and Ford pushed their observations further and further into the outer regions of Andromeda, beyond the bright central bulge and into the faint disk where the surface brightness dropped to levels that previous observers had been unable to reach, the rotation curve refused to behave the way everyone had assumed it would. Instead of falling off in the Keplerian fashion expected if most of the mass were concentrated in the luminous center, the rotation velocity remained roughly constant, or even rose slightly, out to the greatest distances they could measure, as if the galaxy contained far more mass in its outer regions than the visible stars could account for, mass that was exerting gravitational force on the gas and stars orbiting there but that did not shine with any light astronomers could detect. The data accumulated slowly, each observing run adding a few more points to the rotation curve, each new measurement confirming that the flatness of the outer rotation was not a fluke or an artifact of instrumental error, and Rubin and Ford checked their work carefully, aware that such an unexpected result would require solid evidence before other astronomers would take it seriously. The image tube spectrograph was performing as designed, the wavelength calibrations were reliable, and the measurements from different observing runs were consistent with one another, all of which suggested that the flat rotation curve was a genuine property of the Andromeda Galaxy, rather than something their instruments or analysis had somehow created. By the end of the decade, Rubin and Ford had assembled what would become the foundation for one of the most important discoveries in modern cosmology, though the full implications of their data would take several more years to work out and even longer to be accepted by the broader astronomical community. For now, in the quiet offices of the Department of Terrestrial Magnetism and the cold observing floors of mountaintop telescopes, they continued their methodical work, measuring rotation curves and plotting data points, following the evidence wherever it led, even when it led somewhere no one had expected to go. By the early 1970s, Vera Rubin and Kent Ford had settled into a rhythm of patient observation that would, in time, reshape our understanding of the universe, though neither of them could have known this at the outset. Their spectrograph, with its sensitive image tube, had proven itself capable of capturing the faint light from the outer reaches of spiral galaxies, regions that had been difficult or impossible to study with previous instruments, and so they continued their work with the quiet persistence that characterized Rubin's entire career. The Andromeda Galaxy had been their first subject, and the results from that study had been intriguing enough to warrant further investigation, so they turned their attention to other spirals, one by one, gathering data with the same meticulous care that Rubin had brought to all her previous work. Among the galaxies they studied in those early years was Messier 81, a beautiful spiral located approximately 12 million light-years from Earth in the constellation Ursa Major. This galaxy, sometimes called Bode's Galaxy after the astronomer who discovered it in 1774, presented them with an excellent target for observation, being relatively nearby and tilted at an angle that allowed for clear measurements of stellar velocities along its spiral arms. They also observed Messier 33, the Triangulum Galaxy, which lies roughly 3 million light-years away and is one of the closest spiral galaxies to our own Milky Way. Each of these observations required multiple nights at the telescope, and Rubin insisted on repeating measurements to ensure their accuracy, a practice that some might have considered overly cautious but which she regarded as simply good science. The rotation curve of a galaxy, as we discussed in earlier sections, is a graph showing how fast stars and gas orbit at various distances from the galactic center. In our own solar system, the planets follow Keplerian dynamics, named after Johannes Kepler, meaning that objects farther from the Sun orbit more slowly than those closer in. Mercury, the innermost planet, races around the Sun at nearly 50 kilometers per second, while distant Neptune ambles along at just over 5 kilometers per second. This relationship exists because the Sun contains virtually all the mass in the solar system, concentrated at the center, and the gravitational pull weakens with distance according to Newton's laws. Astronomers had long assumed that galaxies would behave in a similar fashion, with most of the mass concentrated in the bright central bulge and the orbital velocities of stars declining steadily as one moved outward toward the dim periphery. What Rubin and Ford found, however, was something quite different. In galaxy after galaxy, the rotation curves remained flat at large radii, meaning that stars at the outer edges of spiral arms were orbiting just as quickly as stars much closer to the center. In the Andromeda Galaxy, stars at a distance of 30,000 light-years from the center were moving at roughly the same velocity as stars at 70,000 light-years, and the curve showed no sign of declining even at the most distant points they could measure. The same pattern appeared in Messier 81, in Messier 33, in NGC 2413, a galaxy lying about 25 million light-years away in the southern constellation Eridanus. The flatness was not a peculiarity of one galaxy or a small sample, but a consistent feature that emerged again and again as they expanded their observations. In 1970, Rubin and Ford published a landmark paper in the Astrophysical Journal presenting their detailed rotation curve for the Andromeda Galaxy. The paper was thorough and carefully argued, presenting velocity measurements at numerous points along the galaxy's major axis, and noting that the observed flatness of the curve was difficult to explain using conventional assumptions about galactic mass distribution. They did not claim to have solved the puzzle in this paper, For Rubin was characteristically cautious about drawing conclusions that went beyond what the data could firmly support. But they made clear that something unexpected was happening in the outer regions of this spiral galaxy. The paper attracted attention within the astronomical community, though not everyone was immediately convinced that the results indicated anything revolutionary about galactic structure. Throughout the mid-1970s, Rubin and Ford continued their observational campaign, adding galaxy after galaxy to their sample. They studied NGC 7541, a barred spiral galaxy located about 30 million light-years away, and NGC 4605, an edge-on spiral that offered particularly clear velocity measurements. They observed NGC 2903, NGC 3198, and NGC 4062, building a collection of rotation curves that grew ever more compelling in its consistency. By 1978, their sample had expanded to include more than 60 spiral galaxies spanning a range of sizes, luminosities, and morphological types, and in nearly every case, the rotation curves remained stubbornly flat at large radii. The pattern was undeniable, even if its explanation remained contested. The interpretation of these flat rotation curves required a significant departure from conventional thinking about galactic structure. If the visible matter in a galaxy, concentrated in the bright central regions, were the only mass present, then Keplerian dynamics demanded that orbital velocities decrease with distance from a center. The fact that they did not decrease implied that there must be additional mass present, mass that was not visible in optical light but which exerted gravitational influence on the orbiting stars. This unseen mass would have to be distributed differently from the visible matter, extending far beyond the bright disk of the galaxy in a vast halo that wrapped around the entire system. The amount of this dark matter, as it came to be called, would have to be enormous, potentially outweighing the visible stars and gas by a factor of 5 or 10 or even more. The astronomical community did not embrace this interpretation immediately. Many researchers were understandably reluctant to accept that most of the matter in galaxies was invisible, a proposition that seemed to violate the principle of scientific parsimony and raised uncomfortable questions about what this dark matter might actually be. Some suggested that the observations might be an error, that systematic effects in the spectrograph or complications in the interpretation of spectral lines might be producing spurious results. Others proposed alternative explanations that did not require hidden mass, such as modifications to Newtonian gravity at large distances or unusual distributions of faint stars in galactic halos. Rubin responded to these criticisms with characteristic patience, re-examining her data, checking for potential sources of error, and continuing to gather more observations that might either confirm or refute her findings. One source of support for Rubin and Ford came from radio astronomers who had been studying galaxies using observations of neutral hydrogen, the most abundant element in the universe. Hydrogen atoms emit radio waves at a characteristic wavelength of 21 centimeters, and by measuring the Doppler shift of this emission, astronomers can map the rotation of gas in galaxies, even where no visible stars are present. Morton Roberts, a radio astronomer at the National Radio Astronomy Observatory, had been conducting precisely such observations, and his results agreed remarkably well with what Rubin and Ford were finding in optical wavelengths. The hydrogen gas, which extended even farther from galactic centers than the visible stars, was also orbiting at unexpectedly high velocities, and the rotation curves derived from radio observations were just as flat as those derived from optical spectroscopy. This convergence of evidence from independent methods and independent observers was crucial in building acceptance for the dark matter interpretation. If Rubin and Ford's results had been due to some instrumental effect peculiar to their spectrograph, the radio observations would not have shown the same pattern. If the flat rotation curves had been a fluke of the particular galaxies they chose to study, other observers using different selection criteria would have found different results. Instead, the evidence pointed consistently toward the same conclusion, that spiral galaxies are embedded in vast halos of unseen matter that dominate their total mass. Rubin collaborated with Roberts and other radio astronomers throughout this period, comparing results and discussing interpretations, in a process of scientific cross-checking that gradually strengthened the case for dark matter. By 1980, Rubin and Ford had refined their analysis and expanded their sample sufficiently to publish what would become a citation classic in the Astrophysical Journal. This paper, titled with the understated clarity typical of scientific literature, presented rotation curves for a large sample of spiral galaxies and argued convincingly that the flat curves implied the presence of massive dark halos surrounding each galaxy. The paper was notable not only for its conclusions but for the meticulous quality of the data it presented, reflecting Rubin's insistence on observing each galaxy multiple times under good conditions to ensure the reliability of every measurement. She had learned from her experiences as a graduate student and young researcher that controversial claims required unassailable evidence, and she took great care to make her evidence as unassailable as she could. The distances to the galaxies in Rubin and Ford's sample ranged from a few million to roughly 100 million light-years, spanning a volume of space large enough to suggest that their findings were representative of spiral galaxies in general, rather than a local peculiarity. NGC 4378, a spiral in the Virgo cluster at a distance of about 55 million light-years, showed the same flat rotation curve as nearby systems. NGC 7664, UGC 2885, NGC 801, and dozens of other galaxies contributed to a portrait of consistency that became increasingly difficult to dismiss. Each galaxy had its own individual characteristics, its own brightness and size and inclination angle, but the flatness of the rotation curves transcended these differences. Rubin's approach to these observations reflected her training and her temperament. She believed that good science required patience and repetition, that a single observation was never sufficient to establish a result, and that the best defense against error was to check and recheck one's work until no reasonable doubt remained. When studying a galaxy, she would return to it on multiple nights, under varying atmospheric conditions, to ensure that her measurements were reproducible. She kept detailed records of every observation, noting the weather, the seeing conditions, the behavior of the equipment, and any other factors that might influence the quality of the data. This meticulousness earned her the respect of colleagues who might otherwise have been skeptical of her unconventional conclusions. The acceptance of dark matter as a major component of galaxies came gradually through the late 1970s and into the 1980s. There was no single moment of revelation, no dramatic announcement that changed everyone's minds overnight, but rather a slow accumulation of evidence and a progressive shift in the scientific consensus. Rubin continued to observe and publish, adding to the body of evidence with each new paper, while theorists began to develop models that could explain the distribution and properties of dark halos. The work of other observers, using both optical and radio techniques, corroborated her findings and extended them to new classes of galaxies. Slowly, reluctantly, the astronomical community came to accept that the universe contained far more matter than could be seen. The implications of this realization were profound, though they were perhaps too large to be fully appreciated at the time. If most of the matter in galaxies was dark, then our inventories of cosmic mass had been dramatically incomplete, and our understanding of galactic structure and evolution would need to be revised accordingly. The nature of the dark matter itself remained a mystery, one that persists to the present day, but its existence seemed increasingly undeniable in the face of Rubin and Ford's patient observations. The flat rotation curves that had seemed so puzzling in the early 1970s had become, by the end of the decade, one of the most important pieces of evidence for a universe far stranger and more complex than anyone had imagined. And so the 1970s drew to a close with Vera Rubin established as one of the leading figures in the study of galactic dynamics, her work on rotation curves recognized as foundational to a new understanding of cosmic structure. The skepticism that had greeted her early results had given way to acceptance, and the flat rotation curves that she and Kent Ford had measured so carefully had become standard knowledge in astronomy textbooks. There would be more work to do, more galaxies to observe, more questions to answer, but the essential discovery had been made, and the universe would never quite look the same again. As the decade of the 1980s began, Vera Rubin found herself in a curious position, one that she had not particularly sought but which arrived nonetheless, in the way that recognition sometimes does after years of quiet and persistent work. The astronomical community, having initially received her findings about flat rotation curves with varying degrees of skepticism and hesitation, had begun to understand that something fundamental had shifted in our understanding of the cosmos, and that this shift owed a great deal to the careful measurements she had gathered night after night at telescopes across the American Southwest. The evidence for dark matter, that invisible substance whose gravitational pull shapes the movements of visible stars while remaining itself unseen, had grown too substantial to dismiss, and Rubin's name had become inseparable from this profound mystery at the heart of galactic structure. In 1981, Vera Rubin received word that she had been elected to the National Academy of Sciences, which is among the highest honors that can be bestowed upon a working scientist in the United States, recognizing not a single achievement but rather a sustained contribution to human knowledge over the course of a career. She was only the second woman astronomer to receive this distinction, following the British-American astrophysicist Margaret Burbidge, who had been elected in 1976 and whose own work on the synthesis of elements within stars had reshaped our understanding of how the universe creates the atoms from which planets and people are eventually made. The fact that in the long history of American astronomy, spanning well over a century of discoveries about the nature of stars and galaxies and the structure of space itself, only 2 women had been deemed worthy of this recognition by 1981 speaks to the particular barriers that Rubin had navigated throughout her life, barriers that she would increasingly choose to address directly in the years that followed her election. The recognition continued to arrive in various forms throughout the early 1980s, each honor bringing with it invitations to speak and opportunities to share not only her scientific findings but also her perspectives on the practice of astronomy as a profession and as a way of life. She received the Dickson Prize in Science from Carnegie Mellon University, which honors scientists whose work has contributed significantly to American scientific progress, and the selection committee noted both her observational achievements and the elegance with which she had approached the problem of galactic rotation. The prize carried with it a certain prestige within the scientific community, the kind that opens doors to further collaborations and ensures that one's telephone calls to observatory directors are returned with a certain promptness. During this same period, Rubin was awarded the Richtmeier Memorial Award from the American Association of Physics Teachers, an honor that recognized not only her scientific contributions but also her ability to communicate complex ideas with clarity and grace, a skill she had developed over decades of explaining her work to audiences ranging from fellow specialists to curious members of the general public who simply wished to understand what all this business about invisible matter actually meant for their picture of the night sky. She approached these speaking engagements with the same methodical care she brought to her observations, preparing her remarks thoughtfully and delivering them in a manner that invited understanding rather than demanding it. Even as these honors accumulated, Rubin continued her research with the same steady focus that had characterized her earlier work, turning her attention to some of the more unusual specimens in the cosmic zoo of galaxy types. Among these were the polar ring galaxies, which are peculiar systems in which a ring of stars and gas orbits around a central galaxy in a plane that is roughly perpendicular to the main disk, creating a structure that looks rather like a spinning top wrapped in a hula hoop, if you will forgive such a homely comparison for so grand a celestial object. These systems are thought to form when two galaxies pass close to one another, and one strips material from the other, with that stolen gas and those captured stars eventually settling into an orbit that preserves the memory of the encounter's geometry. What made polar ring galaxies particularly interesting to Rubin was that they offered a unique opportunity to measure the distribution of mass in 3 dimensions rather than just 2, since the ring and the disk provided rotation curves in perpendicular planes. And by comparing these curves, one could construct a more complete picture of where the dark matter resided within the system. The observations were challenging, as the rings were often faint and the spectroscopy required careful work to separate the light of the ring stars from that of the background galaxy. But this was precisely the sort of patient technical problem that Rubin enjoyed solving, and her collaborations with Kent Ford continued to yield data of exceptional quality. In the mid-1980s, Rubin became involved in a collaboration that would come to be known informally as the Seven Samurai, a group of astronomers who worked together to study the large-scale motions of galaxies in our cosmic neighborhood. The other members of this team included Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, and Roberto Turlovich, each bringing particular expertise to the collective enterprise. Their goal was to measure the peculiar velocities of elliptical galaxies, which is to say the component of their motion through space that cannot be explained by the general expansion of the universe but must instead result from gravitational influences, the pull of mass concentrations that warp the local flow of the cosmic expansion. This work required gathering spectra of many elliptical galaxies and measuring their distances through a method that relied on a relationship between the internal velocities of stars within each galaxy and the galaxy's intrinsic brightness, a correlation that Sandra Faber and Robert Jackson had identified and which came to be called the Faber-Jackson relation. By comparing the predicted distances based on this relation with the observed redshifts that indicated how fast each galaxy was receding, the team could calculate the peculiar velocities and begin to map the large-scale flows of matter in our region of the universe. The collaboration found evidence for a substantial concentration of mass in the direction of the constellation Centaurus, a concentration so massive that it was pulling our own Milky Way and many of our neighboring galaxies toward it, and this structure came to be called the Great Attractor. Rubin's participation in the Seven Samurai collaboration demonstrated her continued engagement with the forefront of astronomical research even as her public profile grew and her responsibilities as a spokesperson for women in science multiplied. She balanced these roles with the same quiet determination she had shown throughout her career, not seeking attention for herself but accepting the obligations that came with her position and using her platform to advocate for those who had fewer opportunities to be heard. Throughout the 1980s and into the early 1990s, Rubin spoke with increasing frequency about the discrimination she had faced during her career and about the systemic barriers that continued to prevent women from participating fully in the astronomical profession. She described the experience of attending conferences where she was the only woman among hundreds of men, of arriving at observatories that lacked restroom facilities for female astronomers because the designers had simply assumed that all observers would be male, of submitting papers and proposals that were judged not on their merits alone but through a lens colored by assumptions about what women were capable of accomplishing in technical fields. She spoke about these experiences not with bitterness but with a clarity of purpose, understanding that her voice carried weight precisely because of the recognition she had earned, and that she could use that weight to create opportunities for those who came after her. In speeches to scientific societies and in conversations with young researchers just beginning their careers, she returned again and again to a central message that she expressed in various forms, but which might be summarized in the words "science progresses best when all are allowed to participate." This was not merely a statement of fairness, though it was certainly that, but also a practical observation about the nature of scientific discovery, which depends on having the widest possible pool of creative minds working on difficult problems, and which loses potential insights whenever talented individuals are discouraged or excluded from the enterprise. Rubin took seriously her role as a mentor to young women astronomers, making time in her schedule to meet with graduate students and postdoctoral researchers who sought her guidance, offering encouragement when the path seemed difficult and practical advice about navigating institutions that had not been designed with their participation in mind. She understood that representation mattered, that seeing someone who looked like you succeeding in a field could make the difference between believing that such success was possible for you and assuming that it was not, and she accepted the responsibility that came with being visible. The specific statistics she cited in her speeches painted a sobering picture of the profession as it existed during those decades. In the early 1980s, women made up only a small fraction of the faculty in astronomy departments at major research universities, often in the single digits, and the numbers were even smaller at the most prestigious institutions. The pipeline was beginning to show signs of improvement at the graduate level, with more women earning doctoral degrees in astronomy and physics than had been the case a generation earlier. But these advances had not yet translated into proportional representation in the permanent positions that shaped the direction of a field. Rubin noted that the attrition occurred at every stage of the career ladder, with women dropping out of the profession at higher rates than men at each transition point, from graduate school to postdoctoral positions, and from postdoctoral positions to tenure-track jobs, and from untenured faculty to the security of permanent appointments. She spoke about the subtle ways in which discouragement could accumulate over a career, the small slights that individually might seem insignificant, but which together created an environment where one constantly felt the need to prove one's belonging. She described the experience of having her ideas attributed to male colleagues in professional settings, of being interrupted in meetings and overlooked for collaborations, of facing questions about her commitment to her work that her male peers with similar family situations did not encounter. These observations were delivered not as complaints but as data, evidence gathered through lived experience and offered in the same spirit of careful documentation that characterized her scientific work. In 1993, Vera Rubin received the National Medal of Science, which was presented to her by President Bill Clinton in a ceremony at the White House that honored scientists and engineers whose work had made exceptional contributions to knowledge and to the welfare of the nation. The award recognized her research on the rotation of galaxies and her role in establishing the observational foundations for the dark matter hypothesis, work that had by this point transformed our understanding of the cosmic inventory and opened new questions that would occupy astronomers for decades to come. Standing in the White House receiving this medal, Rubin represented something more than her individual achievements, though those achievements were substantial enough on their own terms, for she also represented the possibility of recognition for all those who had been told that science was not for them and who had persisted anyway. The National Medal of Science came with renewed attention to both her scientific work and her advocacy, and Rubin used this heightened visibility to continue pressing her message about equity and inclusion in the sciences. She understood that awards and honors, while gratifying to receive, were most valuable when they created opportunities to advance causes larger than oneself, and she approached her role as a public figure with this understanding firmly in mind. The recognition she received during this period, from the National Academy to the Dixon Prize to the National Medal of Science, established her as one of the most honored astronomers of her generation. Yet she remained focused on the work itself and on the obligation she felt to make the path easier for those who followed. Her research on polaring galaxies and her participation in studies of large-scale galaxy motions demonstrated that the honors had not distracted her from the fundamental practice of observation and analysis that lay at the heart of her scientific identity. She continued to visit telescopes and gather spectra, to reduce data and draft papers, to engage with the ongoing conversation about the nature and distribution of dark matter that her earlier work had done so much to stimulate. The sky remained her laboratory, and the questions it posed were far from exhausted, offering a lifetime of puzzles for anyone patient enough to collect the necessary evidence. In the years that followed her formal recognition by the scientific community, Vera Rubin did not slow her pace of inquiry, nor did she retreat into the comfortable quietude that might have tempted another researcher of her standing. Instead, she continued her work at the Carnegie Institution's Department of Terrestrial Magnetism, arriving at her office with the same sense of purpose that had carried her through decades of observation and analysis. The building itself had become a kind of home to her, its corridors familiar, its rhythms predictable, and she moved through it with the ease of someone who had spent the better part of her professional life within its walls. Her office, by this time, had accumulated the evidence of a lifetime spent gazing outward, with star charts pinned to the walls and photographs of galaxies arranged in careful rows, their spiral arms frozen in images that represented light gathered over many patient nights. There were filing cabinets filled with data, notebooks containing handwritten calculations, and on her desk, the ongoing work of understanding the universe continued, one careful measurement at a time. The study of galaxy dynamics remained her primary focus during these later years, though she approached it now with the accumulated wisdom of someone who had already reshaped the field. She was particularly drawn to a phenomenon known as counterrotation, in which certain galaxies exhibited the curious behavior of having their stars and gas rotating in opposite directions. This was not a simple matter to explain, and it suggested complex histories of galactic formation and interaction, of smaller galaxies being absorbed into larger ones, of cosmic collisions that had occurred billions of years before and left their signatures in the motions of matter. Vera found these galaxies fascinating precisely because they were difficult, because they refused to conform to simpler models, and because understanding them required the same careful attention to observation that had always characterized her work. She collaborated with colleagues on these studies, gathering data, analyzing rotation curves, and publishing her findings in the steady stream of papers that continued to emerge from her office well into the 2000s. Her daily routine at Carnegie had a certain gentle regularity to it, shaped by years of habit and by the rhythms of scientific work. She would arrive in the morning, settle into her chair, and begin the process of reviewing data or drafting papers, her concentration unbroken for long stretches of time. The office around her was filled with the accumulated artifacts of her career, and visitors would sometimes pause to take in the photographs of galaxies that lined the walls, each one representing not just a distant object but a chapter in her ongoing investigation of cosmic structure. She kept images of Andromeda nearby, that first galaxy that had captured her attention as a young woman in Washington, and its presence served as a reminder of how far her curiosity had carried her. There were also photographs of colleagues, of family, of the observatories where she had spent so many nights, and together they formed a kind of visual autobiography, a record of a life devoted to understanding the motions of the universe. The work of galaxy formation occupied much of her attention during this period, as she sought to understand not just how galaxies rotated, but how they had come to exist in the first place. This was a question that touched on some of the deepest problems in cosmology, involving the interplay of gravity, dark matter, and the expansion of the universe itself. Vera approached it with the same methodical care she had always applied, gathering observations, comparing them to theoretical predictions, and noting where the two diverged. She was not interested in dramatic pronouncements or sweeping claims, preferring instead the patient accumulation of evidence that had always been her hallmark. Her papers from this period reflect this approach, filled with careful measurements and modest conclusions, each one adding a small piece to the larger puzzle of cosmic structure. Throughout these years, her husband Robert remained her closest companion and most steadfast supporter, their partnership having endured for more than half a century by the time the new millennium arrived. They had built a life together that accommodated both their scientific passions, raising 4 children who had all pursued careers in mathematics and science, and creating a household in which intellectual curiosity was valued above all else. Robert understood, as perhaps few others could, the demands that scientific work placed on time and attention, and he had always encouraged Vera's research, even when it required long nights at distant observatories or extended periods of concentrated effort. Their relationship was one of mutual respect and deep affection, a partnership in which each supported the other's work while maintaining their own intellectual independence. Vera spoke of this support often, acknowledging that her career would not have been possible without his understanding and encouragement. When Robert died in 2008, after 60 years of marriage, the loss was profound. He had been her companion through every stage of her career, from the difficult early years when she had faced discrimination and doubt, through the decades of productive research, and into the recognition and honors that had come later. His absence left a space that could not be filled, and those who knew Vera well observed the depth of her grief. She spoke movingly about what he had meant to her, about the partnership they had built, and about the way his support had made her work possible. In interviews and conversations, she returned often to the theme of their collaboration, not in the scientific sense but in the deeper sense of 2 lives intertwined, each making the other's achievements possible. The foundation he had provided, the quiet encouragement, the practical support that had allowed her to pursue her research while also raising a family, all of this she acknowledged with gratitude and with sorrow at his passing. Even in grief, however, Vera did not abandon her commitment to the next generation of astronomers. She had always been generous with her time and attention when it came to young researchers, and this continued into her 70s and early 80s. She took particular interest in mentoring women who were entering the field, understanding from her own experience the obstacles they might face and the importance of having someone who believed in their potential. She would meet with graduate students and postdoctoral researchers, reviewing their work, offering suggestions, and providing the kind of encouragement that had been so scarce in her own early career. Those who benefited from her mentorship often spoke of her kindness, her patience, and her genuine interest in their success. She did not simply offer advice, she actively worked to create opportunities, writing letters of recommendation, making introductions, and advocating for talented young scientists who might otherwise have been overlooked. The recognition of her work continued during this period, with honors arriving from various corners of the scientific community. In 2002, she received the Gruber Cosmology Prize, which she shared with Kent Ford, her longtime collaborator whose spectrograph had made so much of her research possible. The prize recognized their joint contribution to the understanding of dark matter, acknowledging that their observations had fundamentally altered our conception of the universe. A year later, in 2003, she was awarded the Bruce Medal by the Astronomical Society of the Pacific, one of the most prestigious awards in astronomy, given in recognition of a lifetime of outstanding research. These honors brought her satisfaction, though she accepted them with characteristic modesty, always quick to credit her collaborators and to emphasize the collective nature of scientific discovery. She understood that her work had built on the efforts of those who came before, and she was careful to acknowledge this debt even as she received accolades for her own contributions. She continued to give lectures at universities and public venues during these years, sharing her knowledge with audiences that ranged from professional astronomers to curious members of the general public. Her speaking style was warm and accessible, marked by the same patience and clarity that characterized her writing. She had a gift for explaining complex ideas in terms that non-specialists could understand, for making the rotation of galaxies seem not distant and abstract but immediate and fascinating. Those who attended her lectures often remarked on her ability to convey not just the facts of her research but the wonder that had driven it, the sense of or at the scale and mystery of the cosmos. She spoke of dark matter not as a dry technical subject but as one of the great puzzles of our time, an invitation to further discovery that she hoped would inspire others to pursue careers in astronomy. Her advocacy for women in science never wavered during these later years, even as she received the recognition that had long been denied to her and others. She made a habit of counting the number of women present at conferences and meetings, tracking the percentages over time and noting with concern when progress seemed to stall. She was not content to accept incremental improvements. She wanted to see real change, and she was willing to call out imbalances when she observed them. In her view, the underrepresentation of women in astronomy was not simply a matter of historical bias, but an ongoing problem that required active attention and intervention. She spoke about this issue in interviews, in lectures, and in private conversations, always pressing for greater awareness and more concrete action. Her persistence on the subject was born of her own experience, of the years she had spent being ignored or dismissed, and of her determination that the next generation should not face the same obstacles. The question of the Nobel Prize arose frequently during this period, both in interviews and in the broader scientific community. Many observers felt that Vera's work on dark matter merited the highest recognition, that the evidence she had compiled for the existence of this mysterious substance represented one of the most significant discoveries of the 20th century. Yet the Nobel Committee did not award her the prize, and the absence of this recognition became a subject of comment and controversy. Vera addressed the matter with characteristic grace, expressing disappointment not for herself but for what it signaled about the recognition of women's contributions to science. She noted that no American woman had ever won the Nobel Prize in physics, and she worried that this reflected a broader pattern of undervaluation that extended far beyond her own case. Her concern was not personal ambition but the message that such oversight sent to young women considering careers in physics and astronomy, the suggestion that their work might not receive the same recognition as that of their male colleagues. As the decade progressed, her health began to show signs of decline, though she continued to work for as long as she was able. the body that had carried her through countless nights at the telescope, through decades of research and teaching and advocacy, was beginning to tire in the way that all bodies eventually must. She faced these challenges with the same quiet determination that had marked her entire career, accepting the limitations that age imposed while continuing to engage with the scientific questions that had always fascinated her. Her mind remained sharp, her curiosity undiminished, even as her physical capacities lessened. She continued to read papers, to follow developments in the field, and to maintain connections with colleagues and former students who valued her wisdom and her perspective. The office at Carnegie remained her workspace throughout these years, its walls still lined with the galaxy images and star charts that had accumulated over a lifetime of observation. She would sit at her desk, surrounded by the evidence of her career, and reflect on the mysteries that still remained unsolved. Dark matter, despite all the work that had been done since her early observations, remained fundamentally unknown, its nature a puzzle that continued to elude the most sophisticated instruments and theories. This did not trouble her in the way it might have troubled a less patient researcher. She understood that scientific progress often moves slowly, that some questions required generations to answer, and that the work she had begun would be carried forward by others long after she was gone. There was comfort in this thought, in the knowledge that science was a collective enterprise that transcended any individual life, and that her contributions would remain part of the foundation on which future discoveries would be built. On the morning of December the 26th, 2016, a quiet announcement made its way through the astronomical community, passing from inbox to inbox, from observatory to observatory, carried along by the particular kind of sorrow that accompanies the loss of someone who had changed how we see everything above us. Vera Rubin had died on Christmas Day, in Princeton, New Jersey, at the age of 88, from complications of dementia, and with her passing, the universe lost one of its most patient and persistent observers, a woman who had spent her life looking at galaxies spinning in the dark and finding within their motion a secret that the cosmos had kept hidden for billions of years. The obituaries that followed were remarkable in their consistency, appearing in newspapers and scientific journals across the world, from the New York Times to Nature, from the Washington Post to publications in languages Rubin herself had never spoken, and nearly all of them opened with some variation of the same phrase, calling her the woman who discovered dark matter, or the astronomer who proved the universe was mostly invisible, or simply one of the most important scientists of the 20th century whose contributions had never been recognized with the Nobel Prize she so clearly deserved. These tributes arrived not as the obligatory acknowledgments that sometimes accompany the deaths of elderly scientists long past their active years, but rather as genuine expressions of grief and gratitude from a community that understood just how much she had given them, how thoroughly she had reshaped the landscape upon which they all now worked. Neil deGrasse Tyson, the astrophysicist and science communicator whose voice had become synonymous with public astronomy in America, was among the first to share his reflections, noting that Rubin had pioneered our understanding of the cosmos while simultaneously breaking barriers for women in science, and that she had done both with a grace and determination that made her an inspiration to anyone who believed that careful observation and quiet persistence could reveal truths hidden from those who moved too quickly. Other astronomers followed with their own remembrances, recalling conference presentations where Rubin had asked the most insightful questions, or mentorship conversations that had shaped entire careers, or simply the way she had made space feel welcoming to those who had been told, explicitly or implicitly, that they did not belong there. The American Astronomical Society released a statement describing her as a national treasure, whose work on galaxy rotation curves had transformed our understanding of the cosmos, and whose advocacy for women in science had helped open doors that had been firmly closed to previous generations. Colleagues at the Carnegie Institution, where she had spent most of her career, spoke of her warmth and intellectual generosity, her habit of arriving at the office even in her later years, her genuine interest in the work of younger scientists, and her absolute refusal to be intimidated by the scale of the questions she pursued. Social media platforms filled with photographs of Rubin at various stages of her career, from the young graduate student in the 1950s to the white-haired elder statesperson of astronomy in her final decades. And in each image there was something recognizable, a steadiness in her gaze, a slight smile that suggested she knew secrets about the universe that she was happy to share with anyone patient enough to listen. What struck many of those who wrote about her in those December days was the breadth of her influence, extending far beyond the technical details of rotation curves and mass-to-light ratios into something more fundamental about how science is practiced and who is permitted to practice it. She had shown that one could be a serious researcher and a devoted mother, that one could challenge the established orthodoxy of cosmology while maintaining cordial relationships with those who disagreed, that one could advocate loudly for equity and inclusion without ever becoming strident or unkind. In an era when discussions of women in science often seem to require choosing between professional excellence and personal fulfillment, Rubin had simply refused the choice, raising 4 children while revolutionizing our understanding of the universe, and doing so in a way that made both achievements seem natural, if not easy, then at least possible for those who came after her. Her children survived her, all 4 of them holders of doctoral degrees in scientific fields, a fact that delighted journalists who wrote about her and that Rubin herself had mentioned with evident pride in interviews conducted over the years. David, the eldest, had become a geologist, studying the solid Earth beneath our feet rather than the distant galaxies above, but carrying forward his mother's commitment to patient observation and careful measurement. Judith, her daughter, had pursued cosmic ray physics, working on particles that rain down from space carrying information about violent events in distant corners of the cosmos, a field that shared with her mother's work an interest in the invisible forces shaping our universe. Carl had chosen mathematics, the abstract language underlying all of physics and astronomy, while Alan, the youngest, had followed his elder brother into geology, making the Rubin family a small scientific institution unto itself, spanning disciplines from the theoretical to the observational, from the cosmic to the terrestrial. This remarkable legacy of scientific offspring was no accident, but rather the result of Rubin's deliberate choices about how to structure a life that included both research and family, choices that she discussed openly in interviews and speeches throughout her career. She had spoken frequently about the importance of having a supportive partner, crediting her husband Robert with creating a household where her ambitions were treated as seriously as his own, where children learned from earliest memory that their mother went to work at an observatory and came home with stories about galaxies, where science was simply part of the atmosphere they breathed. She had also spoken about the practical challenges, the need to find childcare, the difficulty of attending conferences when nursing an infant, the guilt that sometimes accompanied leaving children for observing runs that lasted days or weeks, and in discussing these challenges openly, she had helped make them visible in ways that benefited generations of women who came after her. In 2019, 3 years after her death, a recognition came that would have pleased her enormously, though knowing her modesty she might have deflected attention toward the work rather than the honor. The Large Synoptic Survey Telescope, a massive new observatory under construction in the mountains of northern Chile, was officially renamed the Vera Rubin Observatory, making it the first national United States observatory ever named for a woman. The announcement came from the National Science Foundation, which had funded the project, and from the American Astronomical Society, which had campaigned for the honor, and it was accompanied by statements from astronomers around the world who felt that no name could be more appropriate for an instrument designed to map the invisible matter that Rubin had spent her career revealing. The Vera Rubin Observatory sits on Cerro Passion, a mountain peak in the Andes where the air is thin and steady, where clouds rarely gather, and where the darkness at night is among the purest on Earth, undimmed by city lights or industrial haze. Its primary mirror spans more than 8 meters, and its camera contains more than 3 billion pixels, making it capable of photographing the entire visible sky every few nights with a resolution and depth that previous surveys could not have imagined. When it begins its full operations, it will catalog billions of galaxies, tracking their positions and brightnesses over time, watching for the subtle changes that reveal motion and distance and mass, and in doing so, it will create the most detailed map of dark matter ever assembled, showing how this invisible substance is distributed across the cosmos, how it clusters and filaments and voids, how it shaped the universe we see into the patterns we observe. There is something deeply fitting about an observatory devoted to mapping dark matter bearing Vera Rubin's name, for she was the scientist who first showed us clearly that this matter existed, who took the rotation curves of galaxies and demonstrated beyond reasonable doubt that most of the mass in the universe was something we could not see, something that interacted with ordinary matter through gravity alone, something whose nature remains one of the deepest mysteries in all of physics. Every observation the Rubin Observatory makes will be, in a sense, a continuation of her work, an extension of the questions she asked while perched in the prime focus cage at Kitt Peak or Palomar, watching spiral galaxies spin and wondering why their outer stars moved so impossibly fast. Throughout her career, Rubin had a gift for expressing complex ideas in language that was both precise and beautiful, and her words were quoted frequently in the tributes that followed her death. She had said that in a spiral galaxy, the weights come out so that the weights of light do not trace the weights of matter, a simple statement that contained within it a revolution in cosmology. She had observed that we became astronomers thinking we were studying the universe, and now we learn that we were only studying the 5 or 10% that is luminous, a remark that captured both the humility and the wonder of discovering how little we truly knew. And in speaking about women in science, she had noted that fame is fleeting, but my numbers mean more to me than my name, a sentiment that reflected her belief that the work itself mattered more than the recognition it might bring, even as that recognition remained frustratingly elusive throughout her lifetime. Her reflections on women in science were particularly valued by those who came after her, for she had lived through decades when astronomy was dominated by men, when female scientists were rare in faculty positions and rarer still at major observatories, when the barriers were not merely cultural but often explicit and institutional. She had been discouraged from applying to graduate programs, denied access to telescopes, questioned about whether she really belonged in physics rather than some field more suitable for women, and through it all she had persisted, not with anger but with a kind of determined cheerfulness that made her resistance seem almost effortless, though of course it was not. In her later years, she spoke frequently about the progress that had been made and the progress that remained, noting that there were now more women in astronomy than ever before, but that the field remained far from equitable, that the structures which had excluded her generation had evolved but not disappeared, and that continued vigilance and advocacy were necessary if the doors she had helped open were to remain so. She had once said that we have peered into a new world, and have seen that it is more mysterious and more complex than we had imagined. Still more mysterious, she continued, is the reason why our view of nature should be so incomplete, a meditation that applied equally to the dark matter she had discovered and to the biases that had kept so many potential scientists from contributing their insights. The universe, she seemed to suggest, was full of hidden things waiting to be found, and the scientific community was full of hidden talents waiting to be recognized. And the work of astronomy was as much about clearing away the obstacles to seeing as it was about building better telescopes. In the years since her death, her influence has continued to grow, both through the citations of her papers, which number in the thousands, and through the more diffuse but equally important ways that a scientist shapes the culture of their field. Young astronomers who never met her have read her work and absorb her methods, have learned from her example how to approach observations with care and how to follow the data wherever it leads, even when it leads to conclusions that challenge everything their teachers told them. Women in physics and astronomy speak of her as a role model, someone who showed that the path was possible even when it was not easy, someone whose very existence as a successful female astronomer made the next generation's careers slightly less improbable. The Vera Rubin Observatory will soon open its eye to the southern sky, and when it does, it will begin a decade-long survey that will transform our understanding of dark matter, dark energy, and the structure of the cosmos itself. Astronomers will use its data to test theories that did not exist when Rubin was making her observations, to search for answers to questions she would have loved to ask, and to continue the work of mapping the invisible universe that she began with a spectrograph and a willingness to believe what the data told her. Her name will be attached to that work for as long as the observatory operates, and longer still, for names have a way of outlasting the institutions that bear them, settling into the language of science like sediment into stone. And perhaps that is the most fitting tribute of all, that an observatory designed to see what cannot be seen should carry the name of a woman who spent her life teaching us that the universe is mostly hidden, mostly dark, mostly beyond our immediate perception, and that the work of science is to keep looking anyway, to keep measuring and calculating and wondering, until the invisible slowly, gradually, with great patience and care, begins to reveal itself to those who are willing to wait.